Imagine for a moment the profound silence before all sound, the utter darkness before the first flicker of light, and the boundless emptiness before anything existed. For countless centuries, humanity has stared up at the vast, star-peppered canvas of the night sky, wrestling with the most fundamental question of all: how did it all begin? How did our magnificent cosmos, with its swirling galaxies, brilliant stars, and life-giving planets, burst into being from seemingly nothing? It is a question that transcends cultures, religions, and scientific disciplines, a cosmic riddle that continues to captivate and confound us. In our relentless quest for answers, scientists and thinkers have proposed theories so audacious, so mind-bending, they challenge the very fabric of our understanding and push the boundaries of what we thought was possible. Today, we are embarking on an extraordinary journey, a cosmic odyssey that will take us to the edge of time and space, into the very crucible of creation. We are not just scratching the surface, we are diving deep into 25 of the most revolutionary and, yes, often controversial theories about the universe's origin. Forget everything you think you know, because the conventional wisdom about the Big Bang, while a cornerstone of modern cosmology, is just one piece of a much larger, more intricate, and far more mystifying puzzle. We'll explore ideas that suggest our universe might be a mere bubble in an infinite cosmic foam, a holographic projection, or even a cyclical entity that has been born, died, and been reborn countless times. Some theories will stretch your mind to its absolute limits, forcing you to question the very nature of reality, while others will offer glimpses into connections between phenomena we once thought entirely separate. This isn't just a video about science, it's a profound exploration into humanity's insatiable curiosity, our audacious ambition to comprehend the incomprehensible, and our relentless pursuit of truth in the face of profound mystery. Each theory we uncover, no matter how outlandish it may seem at first glance, represents a monumental leap of human intellect, a valiant attempt to piece together the cosmic jigsaw puzzle that surrounds us. So prepare to have your mind expanded, your assumptions challenged, and your sense of wonder ignited. Fasten your seatbelts, because the universe is about to get a whole lot weirder, and your perspective on everything you thought you knew about creation is about to be wonderfully, irrevocably transformed. This is more than just a theoretical discussion. It's an invitation to ponder the biggest questions, to marvel at the unknown, and to join the ongoing human legacy of seeking to understand our place in the grand tapestry of existence. Let's dive into our first mind-bending theory, one that directly challenges the very foundation of our cosmic origin story, the Big Bang, the Big Bounce, or the idea of a cyclic universe. Picture this: instead of a singular, explosive start from nothingness, what if our universe is merely one chapter in an infinite cosmic saga? This theory suggests a universe that's far more resilient, far more dynamic, constantly undergoing an endless ballet of expansion and contraction. Imagine a universe that expands out, reaching a certain point, then begins to slow down, eventually pulling itself back together in a massive gravitational collapse, a cosmic implosion known as the Big Crunch. But here's the twist: instead of ending in oblivion, this Big Crunch becomes the fiery crucible for a new Big Bang, which then propels a new universe into existence, expanding once more. It's an eternal rhythm, a cosmic heartbeat that has been beating for an unimaginable expanse of time, with our current universe being just one beat in this grand, ceaseless symphony. This challenges the very notion of a singular beginning, suggesting that the universe didn't just appear from nothing, but rather transition from a previous state, a prior universe that underwent its own cycle. If this theory holds true, then the question shifts from how did it all begin to how long has this cycle been repeating. It suggests a universe without a true start or an ultimate end, simply a continuous process of rebirth. The implications here are profound, shaking the very foundations of scientific thought that has long relied on the Big Bang as the definitive origin point. It forces us to ask, what evidence, if any, could we possibly find of a prior universe? How would its collapse leave an imprint on our current cosmic structure? And if we can't find direct evidence, what theoretical underpinnings lend credence to such an audacious claim? One of the major hurdles for the Big Bounce theory lies in explaining the universe's current accelerated expansion. For a long time, scientists thought gravity would eventually slow down the expansion, perhaps even reversing it into a big crunch. But then came the discovery of dark energy, that mysterious force pushing galaxies apart faster and faster. If dark energy continues to dominate, our universe might expand forever, becoming a cold, empty void, making a big crunch impossible. This is where the Big Bounce theory faces its most formidable challenge. Proponents of the Big Bounce have to find mechanisms within their models that either prevent dark energy from dominating in the long term or incorporate it into a cycle, perhaps envisioning a universe that expands for an incredibly long time before eventually succumbing to a subtle, unseen force that initiates contraction, setting the stage for the next bounce. It's a complex dance between expansion, dark energy, and the fundamental forces shaping our cosmos. The Big Bounce also neatly sidesteps some of the sticky theoretical problems associated with the Big Bang, such as the initial singularity, the idea that the universe began as an infinitely small, infinitely dense point. In a cyclic model, the universe never truly reaches an infinite density. Instead, it bounces at a finite, though incredibly small and dense, point. This avoids some of the mathematical infinities that plague the standard Big Bang model and offers a more elegant solution to the very beginning, or perhaps the very transition. What it truly means for the universe's ultimate fate, however, remains hotly debated. Does it imply an eternal cosmic recycling plant where everything is constantly being repurposed, or does it hint at a deeper, unknown mechanism that governs these colossal transformations? The Big Bounce offers a compelling, albeit controversial, answer to the universe's grandest questions, inviting us to imagine a cosmos far more cyclical and resilient than we ever dared to believe. This idea of an eternal, bouncing universe also carries immense philosophical weight, particularly when we consider causality and the very arrow of time. If there was no true beginning, but rather an endless succession of universes, then the concept of a first cause becomes slippery. Where does the chain of cause and effect originate if it has always been? It suggests a universe not born, but eternally transforming. And what about the arrow of time, the undeniable progression from past to present to future, often linked to the relentless increase of entropy, the disorder in the universe? In the standard Big Bang model, entropy is constantly increasing, pointing towards a heat death, a cold, empty future where all energy is evenly distributed and nothing can happen. However, the Big Bounce theory offers fascinating ways to grapple with this entropy problem. What if each bounce, each cosmic crunch and rebirth acts as a cosmic reset button? Imagine the universe collapsing into that incredibly dense, hot state, and during this contraction, entropy is somehow reversed or essentially wiped clean, setting the stage for a new, low-entropy universe to emerge from the subsequent bounce. This isn't just about restoring order, it's about a complete thermodynamic renewal, allowing for new stars, galaxies, and perhaps even new life to form in each cycle. Some more radical versions of the Big Bounce even propose that with each new cycle, fundamental constants of nature, like the strength of gravity or the charge of an electron, might subtly change. This opens up the mind-bending possibility that each universe in the infinite sequence could be profoundly different from our own, with different physical laws, different elements, and perhaps entirely different forms of existence. Imagine universes where gravity is so strong that stars burn out in mere moments, or so weak that galaxies never form. It's a truly vast cosmic canvas of endless possibilities. But how do we prove or disprove such a grand cyclical model? That's where the observational challenges become immense. Unlike the Big Bang, which leaves behind echoes like the cosmic microwave background radiation, evidence of a previous universe would be incredibly faint if it exists at all. One line of inquiry involves looking for subtle imprints in the cosmic microwave background itself, tiny anomalies or patterns that might hint at events that occurred before our current universe began to expand. For example, some theories suggest that a prior universe's black holes might leave subtle gravitational waves that could persist through the bounds and be detectable today. Others look for an unexpected smoothness or pattern on the largest scales of the universe, arguing that such features could be relics of a previous cycle that smoothed out irregularities. The sheer scale of the events involved also makes direct observation nearly impossible. We are talking about cosmic collapses and re-expansions that span trillions of years. The traces left behind would be incredibly subtle, like trying to hear a whisper from a distant galaxy. Nevertheless, the pursuit of these faint signals drives cutting-edge research in cosmology, pushing the limits of our observational technology and theoretical understanding. If we could ever find irrefutable evidence of a pre-Big Bang era, it would fundamentally reshape our understanding of existence. It would mean that our universe is not unique, but one iteration in an infinite series, a single pulse in an eternal cosmic heartbeat. The Big Bounce hypothesis, while still speculative, stands as a powerful intellectual counterpoint to the idea of a singular origin, inviting us to consider a cosmos that is not just expanding, but perpetually evolving through an endless cycle of birth, death, and rebirth. It asks us to consider a universe that has always been, in one form or another, continuously transforming. While the Big Bounce offers a cyclical view of physical reality, our next theory takes a radical leap into the very nature of existence itself, the simulation hypothesis. What if everything we perceive, every star, every planet, every thought, every emotion, is not fundamentally real in the way we assume, but rather a meticulously crafted computer simulation? This mind-bending concept suggests that our entire universe, from the smallest subatomic particle to the vast cosmic web of galaxies, is merely a program running on a colossal computer designed by a super-intelligent civilization. It's a truly audacious idea, one that challenges the very fabric of objectivity and asks us to question if we are, in essence, characters in a cosmic game or an elaborate scientific experiment. The arguments for the simulation hypothesis are surprisingly compelling, especially when viewed through the lens of technological progression. Consider our own rapid advancements in computing power and virtual reality. A few decades ago, video games were rudimentary pixelated images. Today, we have hyper-realistic virtual worlds that are almost indistinguishable from reality for those immersed within them. If this rate of technological growth continues, it is not unreasonable to imagine a future where our descendants possess the computational power to simulate entire universes, complete with sentient beings who believe their reality is authentic. Proponents of this theory, such as philosopher Nick Bostrom, argue that if such a civilization is technologically possible, and if they desire to run such simulations, then statistically, it is far more probable that we are living in one of these simulations rather than the one original, base reality. After all, there could be countless simulated universes for every one real one. It's a statistical argument that flips our common sense on its head, suggesting that our universe is just one of an unimaginable number of digital realities. One of the most intriguing pieces of circumstantial evidence cited by simulation theorists is the phenomenon of fine-tuning in our universe. The fundamental constants of physics, like the strength of gravity, the mass of an electron, or the precise value of the cosmological constant, appear to be miraculously calibrated for the existence of life. Even a tiny deviation in any of these values would render the universe inhospitable to stars, planets, and ultimately complex life. This remarkable precision has led some to infer a designer, but in the simulation context, it suggests carefully chosen initial parameters within a program. If you are building a simulation designed to produce life, you would certainly fine-tune the parameters to achieve that outcome. It's like entering specific values into a game engine to ensure the world you create functions exactly as intended. This cosmic fine-tuning, often seen as a mystery in standard cosmology, finds a plausible, albeit unsettling, explanation within the simulation framework. Furthermore, some proponents point to the pixelated nature of reality at the quantum level. Quantum mechanics, the theory that describes the universe at its smallest scales, suggests that reality isn't smooth and continuous, but rather discrete, quantized, and probabilistic. Energy, for example, comes in discrete packets or quanta, and particles can only occupy specific energy levels. Could these fundamental units be analogous to pixels on a screen or the smallest computational units in a program? When you zoom in on a digital image, you eventually see individual pixels. Similarly, when we probe the deepest levels of reality, we encounter fundamental limits and discrete values. This granularity of existence, where there's a smallest unit of space, time, or energy, can be interpreted as a telltale sign that our reality is rendered on a finite computational grid, much like the resolution limit of a computer simulation. And finally, what about glitches or anomalies in our perceived reality? While often dismissed as optical illusions or cognitive biases, some unusual phenomena have been interpreted through the lens of a simulation. Things like the Mandela effect, where large groups of people remember details differently from recorded history, or extremely improbable coincidences, could be seen as temporary rendering errors or patches in the cosmic code. Perhaps even unexplained phenomena, from strange lights in the sky to physics-defying events, might be glimpses of administrators debugging our reality live. Of course, these are highly speculative interpretations, but for those who entertain the simulation hypothesis, they offer intriguing, albeit unproven, possibilities. The underlying idea is that if our universe were a computer program, there would inevitably be limitations, bugs, or even intentional manipulations by its creators. This theory truly forces us to question the very foundation of what we trust as real. While the simulation hypothesis makes us question the very reality of our existence, our next controversial theory takes us back to the universe's physical origins, proposing a truly chaotic and surprising beginning, the primordial black hole theory. Forget the smooth, uniform expansion from a single point that the standard Big Bang model often conjures. What if instead the very early universe was a churning, tumultuous soup of black holes, some astonishingly tiny, no bigger than an atom, others immense, dwarfing our sun? This theory posits that these so-called primordial black holes formed not from the collapse of massive stars, as modern black holes do, but in the immediate aftermath of the Big Bang, within fractions of a second of the universe's birth. The conditions in the very early universe were incredibly extreme, with immense densities and temperatures. It was so hot and dense that vast fluctuations in density, even tiny ones, could have been amplified, causing certain regions to collapse directly into black holes without needing stellar progenitors. Imagine a cosmic pressure cooker where slight variations in uniformity could instantly pinch off into these incredibly compact gravity-dominant objects. These primordial black holes, ranging wildly in size from microscopic to planetary or even stellar mass, would have populated the universe before the first atoms even had a chance to form. This radically alters our picture of the universe's infancy, replacing a smooth, expanding plasma with a dynamic, black hole-rich environment. One of the most compelling aspects of the primordial black hole theory is its potential to solve a major cosmic puzzle, the mystery of dark matter. Dark matter is the invisible substance that makes up about 27% of the universe's mass, influencing galaxies through its gravitational pull, but not interacting with light or other forms of matter. Despite decades of searching, scientists have yet to directly detect the particles thought to constitute dark matter. The primordial black hole theory offers an elegant alternative. What if dark matter isn't some exotic new particle, but simply ordinary matter compacted into these ancient, invisible black holes? Black holes, by their very nature, are dark. They don't emit or reflect light, and their gravitational effects are precisely what we observe for dark matter. If a sufficient number of primordial black holes of the right mass range were formed in the early universe, they could account for all the missing dark matter, providing a neat solution to one of cosmology's greatest enigmas. Furthermore, these tiny, dense relics of the early universe could have played a crucial role in seeding the formation of galaxies. In the Standard Model, tiny density fluctuations in the cosmic microwave background eventually grew into the large-scale structures we see today. But what if primordial black holes acted as initial gravitational anchors, pulling in surrounding matter and accelerating the formation of the first stars and galaxies? A single stellar mass primordial black hole could have acted as a powerful gravitational seed, attracting gas and dust and jump-starting the process of cosmic structure formation much earlier than otherwise expected. This would provide a natural explanation for the remarkably early appearance of massive galaxies that astronomers have observed, which sometimes seem to have formed too quickly for the Standard Model to fully explain. These ancient black holes could have been the scaffolding upon which the cosmic web was built. The existence and behavior of primordial black holes could also explain a variety of high-energy phenomena we observe today. For instance, tiny primordial black holes, those with masses less than about 1 billion metric tons, would be actively evaporating right now due to a theoretical process called Hawking radiation. This evaporation would produce bursts of high-energy particles and gamma rays. While still unconfirmed, some unexplained gamma-ray bursts or mysterious radio signals could potentially be signatures of these evaporating mini-black holes. On the flip side, larger primordial black holes could be responsible for the mergers of supermassive black holes that we now detect through gravitational waves. If a significant population of these ancient, massive black holes exists, their violent collisions throughout cosmic history would send ripples through space-time, which advanced observatories like LIGO and Virgo are now able to detect. Detecting these specific gravitational wave signatures could provide direct evidence for the existence of primordial black holes, transforming this theory from speculation to established fact. However, the primordial black hole theory faces its own challenges and requires precise conditions. The very early universe needed to have just the right amount of inhomogeneity or lumpiness to create these black holes without overproducing them. Too many, and they would dominate the universe's mass too heavily, interfering with observed large-scale structure. Too few, and they couldn't account for dark matter or seed galaxies effectively. Observational constraints based on gravitational lensing, the cosmic microwave background, and the absence of certain gamma-ray signals placed tight limits on the possible masses and abundances of these primordial black holes. Despite these challenges, the primordial black hole theory continues to be a vibrant area of research, offering a tantalizingly chaotic, yet potentially elegant, solution to some of cosmology's most enduring mysteries. It challenges us to rethink the universe's first moments, suggesting a beginning far more violent and black hole, rich than previously imagined. While primordial black holes offer a chaotic start and the big bounce an endless cycle, our next theory takes us into a realm of unimaginable scale and infinite possibilities, eternal inflation and the multiverse. Picture this not as a neat, singular universe, but as an infinite, ever-expanding multiverse, where our observable universe is just one tiny bubble in a frothy cosmic sea. This isn't just a wild idea, it's a profound extension of a concept many cosmologists already accept: cosmic inflation. Inflation theory suggests that in the fleeting moments after the Big Bang, the universe underwent an incredibly rapid, exponential expansion, smoothing out irregularities and stretching space to immense proportions. Eternal inflation takes this idea further, proposing that this inflationary process, once it starts, never truly stops everywhere. Instead, it continuously churns, bubbling off new, pocket universes like ours, each with its own unique characteristics. Imagine a vast background space where inflation is still happening, creating new patches of spacetime that then stop inflating and cool down, forming their own distinct universes. Our universe would be one such cooled-down bubble, and there are potentially an infinite number of others, each emerging from the inflationary foam. The analogy often used is that of an endlessly boiling pot of water, where each bubble that forms and detaches becomes a new universe. This means that space itself is not just expanding, but is eternally generating new cosmic domains. It's a breathtaking vision that drastically redefines our understanding of cosmic scale, moving beyond a single universe to an entire cosmos of universes, each potentially as vast and complex as our own. One of the most compelling reasons to consider the concept of eternal inflation and the multiverse is its potential to address one of the most perplexing mysteries in cosmology: the improbable fine-tuning of our universe's laws and constants. As we discussed earlier, the fundamental parameters of our universe, from the strength of gravity to the mass of subatomic particles, seem to be incredibly precise, almost as if they were perfectly calibrated to allow for the existence of stars, galaxies, and life. If these constants were even slightly different, our universe would be a barren, lifeless place. This delicate balance, often referred to as the fine-tuning problem, has led some to invoke a cosmic designer or sheer luck. However, the multiverse offers a scientific explanation. If there are an infinite number of universes, each with slightly different physical laws and constants, then it's not surprising that we find ourselves in one where conditions are just right for life. In this scenario, our existence isn't a miraculous coincidence, but simply a matter of probability. We wouldn't be here to observe a universe where the laws were inhospitable to life. It's like saying, if you have an infinite number of lottery tickets, it's practically guaranteed that one of them will be a winner. In the multiverse, every possible universe likely exists, or at least a vast number of them, each with its own unique set of physical laws. We just happen to inhabit one that supports our kind of existence. This perspective shifts the question from why is our universe so perfectly suited for life to, given an infinite number of universes, which types of universes are most likely to host intelligent observers. It transforms what appears to be an extraordinary coincidence into a statistical inevitability within a much larger cosmic landscape. The concept of eternal inflation also provides a natural mechanism for generating multiple universes, extending current cosmological models rather than replacing them entirely. It builds upon established principles of quantum field theory and general relativity, incorporating them into a grander, more expansive framework. While direct observation of other universes is currently impossible as they are causally disconnected from our own, the theory predicts certain properties for our universe that are consistent with observations, such as its flatness and uniformity on large scales. The very existence of this inflationary period in our universe, which is widely accepted, suggests the possibility that it didn't just happen once, but could be an ongoing process creating innumerable other cosmic domains. It's a scenario where our universe is literally one bubble among an infinite sea of bubbles, each potentially containing its own unique history and destiny. However, the multiverse theory also faces significant challenges and criticisms. One major concern is its unfalsifiability. If we cannot observe or interact with other universes, how can we ever prove or disprove their existence? Some argue that a theory that cannot be tested isn't truly scientific. Others point to the measure problem, which asks how we assign probabilities to different outcomes in a multiverse, making it difficult to extract concrete predictions. Despite these philosophical and practical hurdles, the concept of eternal inflation and the multiverse remains a compelling and active area of research. It offers a powerful framework for understanding cosmic fine-tuning, pushing the boundaries of what we consider to be the universe, and inviting us to imagine a reality far grander and more diverse than previously conceived. It asks us to consider that our universe, as vast as it seems, might be just an infinitesimal part of something truly boundless. While the multiverse theory expands our universe horizontally, creating endless cosmic bubbles, our next controversial idea twists our understanding of reality in a profoundly different way, turning it inside out, the holographic universe. Imagine for a moment that everything you see, feel, and experience, every star, every galaxy, every three-dimensional object, and even your own body, is not fundamentally three-dimensional at all. Instead, it's merely a projection, a hyper-realistic illusion stemming from information encoded on a distant, two-dimensional surface. This isn't science fiction. It's a radical theoretical concept rooted in some of the deepest mysteries of physics, suggesting that our seemingly substantial, three-dimensional reality might be nothing more than a giant cosmic hologram. The origins of this mind-bending theory trace back to the study of black holes, particularly their thermodynamics. When scientists like Jacob Bekenstein and Stephen Hawking explored how much information a black hole can store, they made a startling discovery. The information isn't proportional to the black hole's volume, as one might expect, but to the area of its event horizon, the two-dimensional boundary from which nothing can escape. This was a profound, counterintuitive insight, leading to the Bekenstein-Hawking entropy, and suggesting that perhaps the amount of information in a region of space isn't limited by its volume, but by its surface area. This idea, known as the holographic principle, proposes that for any given region of space, all the information contained within it can be entirely described by data on its two-dimensional boundary. It's like taking a three-dimensional object and being able to perfectly reconstruct it from a two-dimensional blueprint. This principle gained even more traction with developments in string theory, particularly in a concept called the AD/S/CFT correspondence. This highly technical but incredibly significant duality suggests a mathematical equivalence between a theory of gravity in a specific type of anti-de Sitter AD/S spacetime, which has a curved, negatively hyperbolic geometry, and a quantum field theory CFT without gravity existing on its lower dimensional boundary. In simpler terms, it's like saying that a complex, three-dimensional universe with gravity is mathematically identical to a simpler, two-dimensional quantum theory living on its edge. This correspondence, while initially applied to theoretical toy models of universes, has provided a powerful mathematical framework for exploring the holographic principle and strengthening the idea that our three-dimensional reality could be encoded on a distant two-dimensional surface. It hints that gravity itself, that fundamental force shaping our cosmos, might emerge from the interactions of quantum particles on a boundary. One of the most ambitious goals of the holographic universe concept is to bridge the gaping chasm between quantum mechanics and general relativity. Quantum mechanics describes the world of the very small with incredible precision, but it struggles with gravity. General relativity beautifully describes gravity and the large-scale structure of the universe, but it breaks down at quantum scales, particularly inside black holes or at the Big Bang singularity. The holographic principle offers a potential pathway to unify these two fundamental pillars of physics. If our three-dimensional universe, governed by general relativity and gravity, is merely a projection of a lower-dimensional quantum theory, then this could provide the missing link. It means that the seemingly incompatible descriptions of reality are simply two different sides of the same coin, two different ways of looking at the same underlying information. Gravity, in this view, is not a fundamental force in the same way, but an emergent property, a consequence of quantum information interacting on a boundary. The implications of the holographic universe theory are truly staggering, challenging our most basic perceptions of reality. If our three-dimensional world is just a projection, then what does that say about the fundamental nature of space and time? Perhaps space is not a continuous, infinitely divisible canvas, but emerges from discrete bits of information like pixels on a cosmic screen. Time, too, might be an emergent phenomenon, a sequence of rendered frames rather than a continuous flow. This could explain why time behaves so strangely near black holes, where the very fabric of space-time warps. If our reality is a hologram, it also raises profound questions about consciousness. Are our thoughts and subjective experiences also projections? Is our sense of free will merely part of a sophisticated algorithm? Such questions push the boundaries of philosophy and physics, forcing us to reconsider what it truly means to exist within such a universe. Even more challenging, if our universe is a hologram, could there be holographic noise or subtle clues in our observations? Some scientists are looking for tiny, almost imperceptible distortions in gravitational wave signals or the cosmic microwave background, which might be echoes of this underlying two-dimensional structure. Think of it like trying to discern the pixels on a high-definition screen. While our everyday experience makes the image seem seamless at a fundamental level, it's composed of discrete units. Likewise, if spacetime itself has a granular, pixelated structure due to its holographic nature, it might leave faint signatures that modern detectors are just beginning to be sensitive enough to detect. Such discoveries would revolutionize our understanding of cosmic structure, from the very largest scales down to the smallest. However, such evidence is currently highly speculative, making the holographic universe a compelling, yet still unproven, frontier in theoretical physics. While the holographic universe makes us question what is real and the Big Bounce redefines beginnings, our next controversial theory takes a radically different approach to cosmogenesis, stepping away from gravity as the sole architect of the cosmos, the plasma universe. Imagine a universe not primarily shaped by the gentle, pervasive pull of gravity acting on massive clumps of matter, but by the fierce, energetic dance of electromagnetic forces. This bold idea proposes that the cosmos is fundamentally a plasma phenomenon, a vast dynamic system where electrically charged particles, influenced by powerful magnetic fields, orchestrate the formation and evolution of galaxies and larger cosmic structures. It's a complete paradigm shift, challenging the entrenched gravitational dominance that underpins much of modern cosmology, including the Big Bang model and its reliance on mysterious dark matter and dark energy. Under the plasma universe hypothesis, the universe is filled with enormous, intricate networks of plasma filaments and currents. Think of them as cosmic electrical circuits stretching across unimaginable distances. Plasma, the fourth state of matter, is essentially ionized gas where electrons have been stripped from their atoms, creating a soup of charged particles. Over 99% of the visible matter in the universe is in the plasma state, found in stars, nebulae, and the space between galaxies. Plasma cosmologists, building on the pioneering work of Hans Alfvén, a Nobel laureate in physics, argue that these prevalent electrically charged gases, rather than being mere bystanders, are the active agents shaping the cosmos. They suggest that Birkeland currents, immense electric currents that flow along magnetic field lines, can generate powerful magnetic fields that compress and organize matter, leading to the formation of stars and galaxies. This offers an alternative to gravitational collapse as the primary mechanism for structure formation, emphasizing instead the pinch effect of magnetic fields bringing matter together. One of the most profound implications of the plasma universe theory is its alternative explanation for galaxy formation. In the standard lambda CDM model, galaxies form hierarchically, with smaller structures merging to create larger ones, driven by the gravitational pull of hypothetical dark matter. However, plasma cosmology offers a different narrative. It posits that galaxies could form from the direct condensation of matter within these gigantic plasma filaments, which act like cosmic conduits. The electromagnetic forces within these filaments could naturally sculpt matter into rotating, disk-like structures resembling the spiral galaxies we observe. This would mean that the spiral arms of galaxies, for example, are not merely gravitational remnants of past interactions, but visible manifestations of ongoing electromagnetic activity, with immense currents flowing through them, giving them their characteristic shapes and dynamics. This fundamentally rethinks the cosmic dance, moving from a gravitational ballet to an electromagnetic mosh pit. Moreover, the plasma universe theory attempts to provide explanations for observational phenomena that often necessitate exotic concepts like dark matter and dark energy within the Big Bang framework. For instance, the observed rotation curves of galaxies where stars on the outer edges move faster than expected based on visible matter are a primary piece of evidence for dark matter. Plasma cosmologists propose that these flat rotation curves can be explained by the presence of large-scale magnetic fields and electric currents permeating the galaxies themselves, which exert additional electromagnetic forces on the stars, accounting for their faster rotation without needing invisible dark matter. Similarly, the cosmic microwave background CMB radiation, often hailed as the definitive evidence for the Big Bang, is interpreted differently. While the Big Bang sees it as the afterglow of a hot, dense early universe, plasma cosmologists suggest it could be a result of absorption and re-emission of energy by cosmic plasma, or localized thermalization processes occurring within the vast plasma structures, rather than a relic from a singular initial explosion. Perhaps the most significant challenge the plasma universe theory poses to the Big Bang is its explanation of the cosmic redshift. Edwin Hubble observed that galaxies are moving away from us, and the farther away they are, the faster they recede, leading to the conclusion that the universe is expanding. This expansion causes the light from distant galaxies to stretch, shifting their wavelengths towards the red end of the spectrum, a phenomenon known as redshift. The Big Bang interprets this as direct evidence of a continuously expanding universe. However, some plasma cosmologists following the work of Holton Arp and others suggest that not all redshift is due to cosmic expansion. They propose alternative mechanisms such as tired light theories where photons lose energy during their long journeys through cosmic plasma, or intrinsic redshifts within certain objects themselves, particularly quasars, which appear highly redshifted but are sometimes observed in close proximity to lower redshift galaxies. If a significant portion of redshift isn't due to expansion, then the very foundation of the Big Bang's expansion model is profoundly undermined, and with it, the necessity for a singular explosive origin. The plasma universe theory thus offers a cosmos without a singular Big Bang. Instead, it suggests a universe that has always existed, perhaps in a quasi-steady state, continuously evolving through the interplay of electromagnetic forces and plasma dynamics. There is no beginning from a singularity, no need for inflation, and no need for the mysterious dark matter or dark energy to explain observed phenomena. The universe is active, driven by vast electrical currents and magnetic fields that organize matter on all scales, from stars to galaxies to the largest cosmic filaments. This vision of a universe powered by electricity and shaped by plasma physics stands in stark contrast to the gravity-dominated, expanding universe of the Big Bang, presenting a truly radical and often overlooked alternative to our cosmic origin story. It's a universe that hums with electrical energy, where light and matter are exquisitely intertwined in a dynamic, continuous dance. While the plasma universe hums with electromagnetic energy, our journey now takes us back in time, to a theory that once stood as a formidable rival to the Big Bang itself, one that offers a very different picture of cosmic origins, the steady-state theory. For decades, this view captivated prominent astronomers and physicists, proposing a universe that, despite its observed expansion, remained eternally the same on the grandest scales. Instead of a singular, explosive beginning, the steady-state model envisioned a cosmos without a true start or an ultimate end, one that has simply always been. This wasn't a static universe, it was dynamic, constantly expanding, yet maintaining a consistent average density and appearance over infinite time through a revolutionary concept, continuous creation of matter. Imagine the universe expanding, with galaxies moving further apart, yet new hydrogen atoms spontaneously popping into existence in the vast spaces between them, just enough to fill the growing void and keep the cosmic density perfectly balanced. The appeal of the steady-state theory was immense for several reasons. Philosophically, it offered a universe that was timeless and eternal, avoiding the theological implications or the perplexing singularity of a Big Bang. Scientifically, it provided a seemingly elegant explanation for the observed expansion of the universe without requiring a specific point of origin. Leading proponents like Hermann Bondi, Thomas Gold, and Fred Hoyle passionately championed this view, arguing that the universe should look the same from any point in space and at any point in time, a principle they called the perfect cosmological principle. This meant that what we observe today, the distribution of galaxies, the average density of matter, should be representative of the universe at any past or future epoch. This was a powerful and aesthetically pleasing concept, promising a uniform and predictable cosmos without the messy implications of a unique beginning. It eliminated the need to explain an initial state, a problem that still plagues the Big Bang model. However, the tide began to turn decisively against the steady-state theory with the accumulation of observational evidence, particularly the discovery and confirmation of the cosmic microwave background radiation in 1964. This faint, uniform glow of microwave energy permeating space was interpreted as the leftover heat from a very hot, dense early universe, a direct prediction of the Big Bang model. The steady-state theory struggled to explain the cosmic microwave background. It either had to posit a completely independent mechanism for its existence or dismiss it, neither of which was particularly convincing. Furthermore, observations of distant galaxies also revealed that the universe looked different in the past. There were more quasars and more irregular galaxies in the early universe than there are today, contradicting the perfect cosmological principle. These observations suggested an evolving universe, not a steady one, leading to the widespread acceptance of the Big Bang as the dominant cosmological model. Despite its apparent disproof by the cosmic microwave background, the core ideas behind the steady-state theory were so compelling that some modern variations and extensions attempt to resurrect aspects of it, particularly the notion of continuous creation or an eternally existing cosmos. While not proposing new matter spontaneously appearing everywhere, these modern takes are often subtle and highly theoretical. For example, some models exploring the nature of dark energy, the mysterious force causing the accelerated expansion of the universe, occasionally touch upon ideas that could lead to a quasi-steady state at extremely late times, where the expansion is so rapid that the universe effectively becomes empty and static from the perspective of any remaining matter. Others consider cyclical models like the Big Bounce, which, while having a beginning for each cycle, could be seen as a form of eternal recurrence, a kind of larger-scale steady state. Another area where the spirit of continuous creation subtly surfaces is in attempts to address specific cosmological puzzles, such as the cosmological constant problem, the enormous discrepancy between the vacuum energy predicted by quantum field theory and the much smaller value observed in nature. Some speculative theories propose mechanisms where spacetime itself might be continuously generated or transformed, influencing the effective value of vacuum energy, or leading to subtle, ongoing processes that resemble a form of creation at a fundamental level. Furthermore, the apparent age crisis of certain distant objects, galaxies or quasars that appear to be older than the universe should be at their observed redshift according to standard cosmological models, sometimes leads researchers to briefly consider alternatives that allow for greater cosmic duration or different rates of evolution for matter at very early times. While these are not direct returns to the classical steady-state theory, they demonstrate that the allure of a universe without a definitive beginning, or one that continuously regenerates itself, persists in the minds of some cosmologists, pushing the boundaries of what is considered possible within the cosmic framework. While the steady-state theory flirted with continuous creation on a grand scale, and the plasma universe sees matter organized by electromagnetic forces, our next controversial theory offers a truly bizarre, almost biological explanation for cosmic origins, the fecund universes, or Lee-Smolens's theory of cosmological natural selection. Imagine for a moment that black holes, those enigmatic cosmic devourers, are not just gravitational dead ends, but instead act as the ultimate cosmic wombs, birthing new baby universes. This theory proposes that every time a black hole forms in our universe, it creates a new, entirely separate universe on the other side, with slightly altered physical constants. It's a truly audacious concept, suggesting that the cosmos evolves through a process remarkably akin to biological reproduction and natural selection, where universes reproduce and mutate over cosmic time. The core idea here is that universes capable of forming more black holes are more successful in this cosmic evolutionary struggle. Think of it like a biological species. Organisms that are better adapted to their environment reproduce more successfully, passing on their genes. In Smolens's model, universes that have physical laws and fundamental constants that are finely tuned for the efficient production of black holes will, by definition, create more black holes. Each of these black holes then acts as a progenitor for a new universe, ensuring that those successful universal properties are propagated. Over countless generations of universes, this process would lead to a kind of natural selection, favoring universes with constants that optimize black hole formation. This mechanism beautifully ties together the seeming fine-tuning of our universe's constants, for example, the strength of gravity, the mass of protons, or the charge of an electron, to the very act of cosmic reproduction. It suggests that our universe is not just randomly fine-tuned for life, but specifically for black hole production, and life is simply a happy byproduct of those conditions. This theory offers a compelling, albeit indirect, explanation for the apparent fine-tuning of our universe's fundamental constants. For instance, the values of our universe's constants are perfectly suited for the formation of stars, which are the precursors to black holes. If gravity were slightly stronger, stars would burn too quickly and collapse into black holes almost instantly, leaving no time for complex chemistry or life. If gravity were too weak, stars and galaxies might not form at all, meaning no supernovas and thus no black holes. Our universe seems to exist in a Goldilocks zone where star formation and subsequently black hole formation is incredibly efficient. Smolens argues that this efficiency isn't just a lucky break, it's the result of eons of cosmic evolution. Universes where constants were not conducive to black hole formation would simply have fewer offspring, eventually dying out of the cosmic lineage. Our universe, therefore, is a descendant of a long line of black hole-producing universes optimized for this very process. The implications for the origin of life within this framework are profound. If the universe evolves to maximize black hole production, and if black hole production is intrinsically linked to star formation and the complexity of matter, then life could be seen as an incidental yet beautiful consequence. The conditions that allow for stable stars, heavy elements, and planetary systems, all prerequisites for life, are often the same conditions that are excellent for forming black holes. This provides an elegant, albeit unsettling, answer to the anthropic principle, which often observes that the universe just happens to have the right conditions for life. Smolin's theory flips this by saying the universe isn't fine-tuned for life, but for black holes, and life just happens to ride along with that optimization. It's a universe that, in a sense, breeds itself into existence through a continuous cascade of black hole creations, each potentially giving rise to a new reality. One of the most intriguing aspects of the fecund universe's theory is that it makes testable predictions, a key characteristic of any scientific theory. For example, Smolin suggests that if his theory is correct, then the values of the fundamental constants in our universe should be optimized far more for black hole production than for any other cosmic phenomenon. Researchers could analyze the parameters of our universe and calculate whether they are indeed maximally conducive to black hole formation. If we found a universe that theoretically could produce even more black holes than ours with different constants, it would pose a significant challenge to the theory. Furthermore, it implies that certain types of black holes, those most efficient at spawning new universes, should be particularly prevalent in our cosmos. This opens up avenues for observational astronomy, where we can test the distribution and types of black holes we observe, looking for patterns that might hint at a universe shaped by this cosmic evolutionary process. However, like any truly groundbreaking theory, the fecund universe's concept faces considerable criticism and unresolved questions. The mechanism by which a black hole spawns a new universe is highly speculative and currently lacks a solid foundation in quantifiable physics, often requiring excursions into realms like quantum gravity where our understanding is still nascent. How exactly does the information or energy pass through the singularity to create a new universe? What determines the subtle mutations in the constants of the new universe? These are immense challenges for the theory to overcome. Despite these hurdles, Smolin's idea remains a fascinating and provocative alternative to the more conventional explanations for cosmic fine-tuning. It provides a unique blend of cosmology, quantum physics, and evolutionary biology, daring us to imagine a universe that isn't just expanding or cyclical, but actively reproducing and evolving, with black holes as the very engines of creation, generating an endless lineage of new cosmic realities. While the fecund universe's theory imagines black holes as cosmic birthplaces in a very abstract reproductive sense, our next controversial idea proposes a far more literal, explosive role for a theoretical counterpart, the white hole as universe creator. If black holes are cosmic drains, relentlessly pulling in matter and energy towards an inescapable singularity, what if there's an opposite phenomenon, a cosmic geyser, violently spewing out matter and light seemingly from nowhere? This is the elusive and purely theoretical concept of a white hole. Think of it as a time-reversed black hole, an exit point in spacetime that cannot be entered from the outside, only left. Though their existence remains purely hypothetical and highly challenging to the established rules of general relativity, some audacious theories speculate that these enigmatic entities could be the ultimate cosmic connectors, or perhaps even the very origin points of new universes, including our own. The mathematical basis for white holes emerges directly from Einstein's theory of general relativity, specifically from the same equations that predict the existence of black holes. If you mathematically reverse the flow of time in a black hole solution, you get a white hole. Just as a black hole has an event horizon beyond which nothing can escape, a white hole has an event horizon beyond which nothing can enter. Instead of crushing matter, it violently expels it. However, unlike black holes, for which we have abundant observational evidence, there is currently no direct observational evidence for white holes. Their existence poses significant theoretical challenges. For instance, creating a white hole would require highly unusual initial conditions that current physics models struggle to explain. How would a white hole form? There's no known physical process that could create one, as they would violate the second law of thermodynamics by spontaneously decreasing entropy. Nevertheless, their mathematical possibility continues to intrigue physicists, prompting speculation about their potential role in the cosmic landscape. One of the most intriguing, albeit highly speculative, roles for white holes in universe creation is their connection to black holes themselves, forming what's often referred to as a wormhole or an Einstein-Rosen bridge. Imagine the singularity at the heart of a black hole not as an absolute end, but as a gateway. According to this extreme interpretation, the matter and energy that fall into a black hole in one universe don't just disappear. They traverse a theoretical tunnel through space-time and re-emerge through a white hole in another region of space-time, or even in an entirely different universe. In this mind-bending scenario, every black hole in our universe could potentially be feeding new matter and energy into a nascent universe on the other side, effectively making them cosmic umbilical cords. This would imply a continuous cycle of creation and consumption, linking universes in a vast, interconnected network. Our own Big Bang, in this view, might not have been an absolute beginning, but instead the spectacular eruption of a white hole, the grand entrance for matter from a parent universe, spewing out the initial conditions for our cosmos. This audacious idea offers a tantalizing solution to the problem of the Big Bang singularity. Instead of our universe emerging from an infinitely dense, perplexing point of infinite energy and zero volume, it would emerge from the other side of a black hole singularity. The matter and energy that constitute our universe would have originated from an earlier, distinct universe, processed through a black hole and then recycled through a white hole. This concept of cosmic recycling provides a continuous flow of existence, avoiding the necessity of creation from absolute nothingness and offering a mechanism for the transfer of matter and energy across cosmic boundaries. It also subtly connects to the concept of the multiverse, suggesting a form of inter-universal travel or creation, where black holes act as the cosmic midwives. The universe becomes a grand, dynamic system of interconnected births and deaths, a web of universes perpetually linking through these exotic space-time gateways. However, the challenges to this theory are immense and numerous. The stability and traversability of such wormholes are highly questionable. Theoretical models often suggest they would be incredibly unstable, collapsing too quickly for anything to pass through. Furthermore, the very existence of white holes contradicts our current understanding of the direction of time and the increase of entropy. Nevertheless, the mathematical beauty of their existence within general relativity continues to fuel speculative models. Some researchers even propose that the Big Bang itself could be considered a type of white hole event, a sudden, explosive emergence of all matter and energy from a point in space-time that cannot be entered. While this doesn't fully explain what caused the white hole or where the material came from, it reframes the origin event from a mysterious singularity to a process of ejection. This conceptualization pushes the boundaries of our imagination, suggesting that perhaps the most destructive forces in our universe, black holes, are also intimately tied to the most creative, giving birth to entire new realities. While the white hole theory suggests a violent, almost instantaneous cosmic birth from another universe, our next controversial idea offers a far more elegant, almost philosophical take on how universes might succeed one another. Imagine a universe that doesn't just expand and die, but subtly transforms its infinitely distant future into the fiery beginning of a brand new cosmos. This is Sir Roger Penrose's conformal cyclic cosmology, a mind-bending theory that posits an endless sequence of eons, with the end of one becoming the start of the next, erasing the need for a singular, absolute beginning. It's a universe that perpetually recycles itself, not through a violent crunch and bounce, but through a gradual, almost imperceptible transition across cosmic scales. At the heart of conformal cyclic cosmology is a deep mathematical insight related to the concept of conformal geometry. Penrose argues that in a universe dominated by expansion as matter spreads out and black holes evaporate over incomprehensibly long timescales, the universe effectively becomes empty and radiation-dominated. In this state, everything remaining is massless photons, gravitons, and potentially other exotic particles. Crucially, Penrose points out that at this infinitely distant future point, the concept of scale loses meaning. A universe composed entirely of massless particles looks exactly the same conformally, regardless of its overall size. This means that the infinitely expanded, infinitely diluted future of one eon becomes conformally equivalent to the incredibly dense, singular state of the Big Bang of the next eon. In essence, the infinitely stretched out end of one universe smoothly grafts onto the beginning of another, creating an endless chain or eon of cosmic existences. The universe doesn't explode into being from nothing. It simply transitions from a previous state where the fundamental laws of physics can be mapped from one eon to the next. This theory offers a unique solution to several perplexing problems in standard cosmology, particularly the initial singularity of the Big Bang and the problem of cosmic entropy. In the classical Big Bang model, the universe bursts into existence from an infinitely dense point, a singularity where physics breaks down. Conformal cyclic cosmology elegantly bypasses this by suggesting that what we perceive as the Big Bang singularity is simply the conformally rescaled, infinitely expanded past of a previous eon. There's no true singularity in the sense of a beginning from nothing. Instead, it's a phase transition. Furthermore, it addresses the entropy problem. In each eon, entropy increases, leading to a state of maximum disorder. However, when the universe becomes infinitely dilute and dominated by massless particles, the fundamental measure of entropy itself undergoes a transformation, allowing the next eon to begin from a state of low effective entropy, ready for new structure formation. It's a cosmic reset, but one that occurs through a seamless mathematical transition rather than a violent collapse and rebound. One of the most audacious predictions and claims of conformal cyclic cosmology comes from Penrose himself, who suggests we might find direct evidence of previous eons embedded within our own. Specifically, he has claimed to detect what he calls Hawking points in the cosmic microwave background, the faint afterglow of the Big Bang. These Hawking points are purported to be anomalous circular patterns in the temperature fluctuations of the background radiation. Penrose posits that these circular patterns could be the minute, superheated imprints left by supermassive black holes from the previous eon, which would have emitted enormous amounts of energy through Hawking radiation as they finally evaporated in their infinitely distant future. The energy from these evaporating black holes would have crossed the eon boundary and left a detectable signature in the early universe of our current eon. If confirmed, this would be revolutionary, providing a direct observational link to a universe that existed before our own. However, these Hawking points remain highly controversial and are not widely accepted by the broader cosmological community. Many cosmologists attribute these patterns to statistical fluctuations within the cosmic microwave background data or systematic errors in analysis, rather than genuine relics of a prior eon. The statistical significance of these observations is still hotly debated, and independent verification has proven elusive. The idea of information, even in the form of energy, crossing the boundary between eons also presents significant theoretical challenges within the framework of quantum gravity. Nevertheless, Penrose continues to champion his theory, arguing that the standard Big Bang model leaves too many unanswered questions about the universe's initial state, and that conformal cyclic cosmology provides a more complete and mathematically consistent picture of cosmic evolution. It challenges us to reconsider the very nature of time, beginnings and endings, daring us to imagine a universe that has always been, simply transforming its incredibly distant future into a new present in an endless, elegant cosmic dance. While conformal cyclic cosmology elegantly dissolves the Big Bang singularity by mathematically stretching one eon into the next, our next controversial theory dives deep into the very fabric of spacetime, proposing a quantum solution to the universe's ultimate beginning, loop quantum gravity and the Big Bounce. Imagine not a smooth, continuous spacetime, but one woven from tiny, discrete loops like an incredibly fine cosmic fabric. This is the revolutionary insight of loop quantum gravity, or LQG, an ambitious attempt to unite general relativity, the theory of gravity and large-scale structure, with quantum mechanics, the physics of the very small. Unlike string theory, which posits fundamental vibrating strings, LQG suggests that space and time themselves are granular, pixelated at an unimaginably tiny scale, composed of fundamental quanta of space and time. This granular nature of space-time profoundly changes our understanding of what happens at the universe's extreme edges, particularly at the Big Bang. In the standard Big Bang model, the universe began from an infinitely dense, infinitely small point, a singularity where the laws of physics break down. This is akin to dividing by zero in mathematics. It's a theoretical problem that physicists have long grappled with. However, loop quantum gravity offers a radical, elegant solution. Because space itself is quantized, there's a smallest possible volume, a minimum size that spacetime can shrink to. It simply cannot collapse to an infinite density or an infinitesimal point. This means that instead of a singularity, the LQG framework predicts a Big Bounce. Rather than exploding into being from nothing, our universe emerged from the collapse of a previous universe that contracted to a minimum, incredibly dense but finite, volume before bouncing back out into the expansion we observe today. Think of it like a cosmic trampoline. The universe collapses down, but instead of hitting an infinitely hard floor, the singularity, it compresses to its absolute minimum allowable quantum size, then springs back, expanding again. This completely circumvents the troublesome infinite density problem that has plagued the traditional Big Bang theory for decades. It suggests a smooth, albeit incredibly dramatic, transition from a contracting previous universe to our expanding one, replacing a mysterious point of infinite curvature with a well-defined physical event. This isn't just a theoretical tweak, it fundamentally reshapes our understanding of cosmic beginnings, implying that the universe never actually reaches a state of infinite density, making its history continuous and potentially eternal. It's a profound shift from a singular point of creation to a moment of cosmic transition, where a universe simply changes phase. The implications of LQG's Big Bounce are far-reaching. If our universe emerged from a previous contracting universe, then it opens up the fascinating possibility that relics or imprints from that pre-Big Bang state might exist within our current cosmos. While the bounce would likely erase much of the detailed information, certain fundamental properties or large-scale structures could potentially pass through the bounce and leave subtle signatures in the cosmic microwave background radiation or in the distribution of galaxies. Researchers are actively exploring what these potential echoes of a prior universe might look like, searching for anomalies or patterns that deviate from the predictions of a universe that began from an absolute singularity. For example, some models suggest that the curvature of spacetime or certain early universe symmetries might subtly reflect the conditions of the preceding contracting phase. This means that by studying our universe, we might be able to peer into the past, not just of our own expansion, but into a prior cosmic iteration. Furthermore, the Big Bounce in LQG offers a compelling solution to the origin of cosmological inflation, the rapid expansion that proponents of the standard Big Bang model invoke to explain the universe's flatness, homogeneity, and the absence of magnetic monopoles. In many LQG bouncing models, the conditions generated by the bounce itself, a sudden, violent decompression and expansion from an extremely dense state, naturally lead to a period of inflation without needing to introduce a separate, hypothetical, inflaton field. The dynamics of the quantum spacetime itself as it rebounds provide the necessary force for this exponential growth. This offers a more unified picture where the bounce generates the very conditions that lead to the subsequent cosmic evolution. It connects the earliest moments of the universe to its subsequent rapid expansion in a more integrated manner, suggesting that the inflationary period is a natural consequence of the bounce rather than a separate, ad hoc addition to the model. However, loop quantum gravity and its big bounce prediction remain an active and evolving area of research, not without its challenges. It is still a theoretical framework, and directly observing the quantum nature of space-time or the precise moment of the bounce is beyond our current technological capabilities. Furthermore, while LQG provides a robust framework for quantum gravity, fully connecting its predictions to the large-scale universe we observe and deriving detailed, falsifiable observational predictions is an ongoing and complex task. The mathematical details and the precise mechanisms by which information might pass through the bounce are still being refined. Despite these hurdles, LQG offers a profound, singularity-free vision of cosmic origins, suggesting our universe is part of an endless cosmic cycle, a continuous dance of contraction and expansion, where the fabric of spacetime itself is the ultimate cosmic resilient material, perpetually rebounding into new existence. While loop quantum gravity offers a quantum big bounce, our next controversial theory takes us into even stranger dimensions, proposing a truly mind-bending origin story, the ekpyrotic universe. Imagine our universe didn't emerge from a singular, infinitely dense point, but from a cataclysmic collision between two vast, hidden, multi-dimensional membranes or branes floating in a higher dimensional space. This theory, rooted deeply in the complex mathematical framework of string theory, suggests that the Big Bang was not the absolute beginning of spacetime itself, but rather a violent, fiery event resulting from such an interdimensional crash. It's a cosmic origin story that replaces an explosive point with an epic, hyperdimensional smash-up, fundamentally redefining what the beginning even means. At its core, the ekpyrotic universe concept posits that our three-dimensional universe, along with potentially many others, exists as a brane within a larger, invisible, higher-dimensional space, often referred to as the bulk. Think of it like sheets of paper floating in a room. We, and all the matter and forces we observe except gravity, which is thought to be able to extend into the bulk, are confined to one of these sheets, our brane. Another unseen brane might be lurking nearby. The ekpyrotic model suggests that these two branes, after a long, slow period of approach, eventually collide. This collision releases an enormous amount of energy, creating the matter and radiation we see in our universe and setting off the expansion we call the Big Bang. But crucially, in this model, the Big Bang is not the creation of spacetime from nothing. It's a cosmic event within an already existing, larger reality. This means that the universe existed long before the Big Bang in a different, perhaps contracting, phase, quietly drifting towards its inevitable cosmic smash-up. One of the most compelling aspects of the ekpyrotic model is its potential to naturally explain some of the cosmological puzzles that the standard Big Bang theory often struggles with, or requires additional theoretical constructs to resolve. Two significant examples are the flatness problem and the horizon problem. The flatness problem refers to the extraordinary precision with which our universe's geometry appears to be perfectly flat, meaning its energy density is incredibly close to a critical value. The horizon problem refers to the observation that widely separated regions of the cosmic microwave background, which never had time to causally interact in the standard Big Bang model, still exhibit remarkably uniform temperatures. The standard inflationary theory was developed to address these issues. However, the ekpyrotic model offers an alternative mechanism. During the slow approach of the two branes, any initial inhomogeneities or curvature are naturally smoothed out as the branes draw closer. This long, gradual, pre-Big Bang phase allows ample time for different regions to communicate and thermalize, leading to the observed uniformity and flatness of our universe without needing a rapid, exponential inflationary burst immediately after the crash. Furthermore, the ekpyrotic model attempts to resolve the problematic singularity of the Big Bang. In the traditional view, the universe began as an infinitely dense point, a mathematical singularity where the laws of physics break down. In the brane collision scenario, the Big Bang is not a true singularity. Instead, it's a moment of incredibly high but finite density and temperature resulting from the brane impact. The universe never actually collapses to an infinite point. Rather, it transitions smoothly through the collision point from a previous contracting phase to our current expanding phase. This offers a more physically palatable picture of cosmic origins, avoiding the mathematical infinities that plague the standard model and providing a continuous, albeit dramatic, trajectory for the universe's evolution. It suggests that the Big Bang was more of a big crash than a big bang from nothing. The theory also naturally leads to a cyclical universe, much like the Big Bounce. After the branes collide and our universe expands, it eventually stretches out and thins, becoming effectively empty again. This expansion then sets the stage for a new, slow approach of the branes, leading to another collision and another Big Bang. This creates an endless cycle of contraction, collision, and expansion, with our universe being just one iteration in an infinite series of cosmic events. This offers a profoundly different perspective on cosmic time, suggesting that the universe has no absolute beginning or end, but is instead perpetually renewing itself through these dramatic interdimensional impacts. Each crash, each ekpyrotic fire, gives birth to a new eon of cosmic expansion, carrying forward the fundamental laws of physics that govern brane interactions. However, the ekpyrotic universe theory, while elegant, faces significant challenges and remains highly speculative. It relies on the existence of extraspatial dimensions and the complex mathematics of string theory, neither of which has yet been directly observed or experimentally verified. The precise mechanisms of brane collision and the transfer of energy into our visible universe are still being developed and refined, proving the existence of such a multi-dimensional bulk and other branes is currently beyond our observational capabilities, making it difficult to test directly. Furthermore, some versions of the theory struggle to fully account for the precise spectrum of density fluctuations observed in the cosmic microwave background, which are better explained by inflationary models. Despite these hurdles, the ekpyrotic universe offers a captivating and truly exotic alternative to the standard Big Bang model, challenging us to consider a cosmos far more intricate and multi-layered than we typically imagine, where our universe is merely a spectacular ripple in an unseen, higher-dimensional sea. While the ekpyrotic theory sees universes colliding in higher dimensions, our next controversial idea offers a profoundly different, almost constantly fractal view of cosmic creation, not as a singular event but as an ongoing, infinite process, the many worlds interpretation. This isn't a theory about how the universe began from nothing, but rather how new universes are continuously born moment by moment from within our own. Imagine that every single time a quantum event occurs, an electron jumping energy levels, an atom decaying, a photon hitting a detector, the universe doesn't just make a choice. Instead, it literally splits or branches into parallel realities, each representing a different possible outcome of that event. This radical concept, primarily an interpretation of quantum mechanics, implies an endlessly branching cosmic tree, generating an infinite number of parallel universes, right here, right now, with every quantum flicker. The origins of the many worlds interpretation, or MWI, lie in the perplexing nature of quantum mechanics, the very successful but deeply counterintuitive theory that governs the subatomic world. In quantum mechanics, particles don't have definite properties until they are measured. Before measurement, they exist in a superposition of all possible states simultaneously. For example, an electron isn't just here or there, it's potentially both until an observation forces it to choose. The standard interpretation, the Copenhagen interpretation, suggests that the act of measurement collapses this superposition into a single, definite reality. But the MWI, first proposed by Hugh Everett III in 1957, offers a different solution to this measurement problem. It posits that there is no collapse. Instead, every possible outcome of a quantum measurement is realized, but in different, non-interacting branches of the universe. When the electron is observed, our universe doesn't pick a state. It splits into two or more parallel universes, one where the electron is here and another where it's there. And we, the observers, split along with it, experiencing only one of those realities. This continuous branching means that the universe we experience is just one tiny twig on an unimaginably vast, constantly growing cosmic tree. Every time you make a decision, every time a photon interacts with an atom, every time a subatomic particle flips a spin, a new universe is born that represents every alternative outcome. This challenges the very notion of determinism. If every possible outcome happens in some universe, then is anything truly determined? It suggests that free will, in its conventional sense, might be an illusion. While we only perceive one path, all possible paths are being actualized in parallel realities. It also has profound implications for consciousness. If we split with every quantum event, then an infinite number of yous exist in these parallel branches, each experiencing a slightly different history. This means that every choice you didn't make, every road not taken, is being lived out by another version of you in another universe. It's a dizzying thought, transforming our universe into a fractal cosmic engine, perpetually generating new realities, making the concept of a single, unique origin point for the cosmos far less meaningful. One of the most appealing aspects of the many worlds interpretation for many physicists is its elegant simplicity and its mathematical rigor. Unlike other interpretations, it doesn't require an ad hoc collapse mechanism for the wave function, nor does it carve out a special role for conscious observers. It takes the equations of quantum mechanics literally. If the Schrödinger equation describes the evolution of a quantum system over time and doesn't explicitly include a collapse, then all possible outcomes must continue to evolve. The MWI simply takes this natural evolution to its logical conclusion, implying that all branches of the wave function are equally real. This no-collapse approach allows for a cleaner, more consistent mathematical description of quantum reality, avoiding the philosophical complexities and ambiguities of the Copenhagen interpretation. It suggests that the underlying quantum physics of the universe is unitary, meaning it evolves smoothly and predictably without any random, non-deterministic jumps. The apparent randomness we observe is simply a consequence of our limited perspective within one of the many branches. However, the many worlds interpretation also faces significant criticisms and philosophical hurdles. The sheer extravagance of an infinite number of universes, most of which are unobservable and causally disconnected from our own, troubles many scientists who prefer more parsimonious explanations. If we can never interact with these parallel branches, how can we ever prove or disprove their existence? This leads to the fundamental question of falsifiability, a cornerstone of scientific inquiry. Critics also point to the basis problem and the preferred basis issue. How do these universes branch, and what determines the specific properties that distinguish one branch from another? While decoherence, the process by which quantum systems lose their quantum properties through interaction with their environment, offers some answers. The precise mechanism of branching and how distinct worlds emerge from the quantum wave function remains an active area of debate. Furthermore, the implications for probability are complex. If every outcome happens, what does it mean to say one outcome is more probable than another? Despite these challenges, the many worlds interpretation continues to be a vibrant and influential area of research, gaining increasing traction among quantum physicists. Its elegance in resolving the measurement problem and its consistency with the fundamental equations of quantum mechanics make it a compelling, albeit controversial, candidate for understanding the nature of reality. While it doesn't describe the absolute beginning of the universe in the classical sense, it proposes an ongoing, continuous process of cosmic creation, where new universes are perpetually brought into being with every interaction at the quantum level. It forces us to ask, if every possibility truly plays out in some universe, what then does that imply about the nature of our own existence and the true extent of reality? Is our universe merely one thread in an infinite, ever-expanding tapestry of possibilities, constantly weaving itself wider with every passing moment? While the many worlds interpretation suggests an endless branching of existing realities, our next controversial theory delves into the most fundamental question of all: can the universe create itself from nothing? This is the mind-bending concept of the self-creating universe, often referred to as the cosmic bootstrap. It's an idea that challenges our intuitive understanding of cause and effect, proposing that our entire cosmos, with all its matter, energy, space, and time, could have spontaneously arisen from what seems like an ultimate void, given enough time and the right fundamental laws. This isn't about an external creator, it's about the universe being its own origin, pulling itself into existence by its own inherent logic. At the heart of this audacious idea lies a redefinition of nothing. When physicists talk about the universe arising from nothing, they're usually not referring to absolute philosophical nothingness, a void so empty it doesn't even contain space or time. Instead, they're often referring to the quantum vacuum. In classical physics, a vacuum is just empty space, but in quantum mechanics, the vacuum is a seething, effervescent foam of activity, brimming with virtual particles constantly popping into and out of existence, obeying the Heisenberg uncertainty principle. These ephemeral particles exist for fleeting moments, borrowing energy from the vacuum before vanishing again. The self-creating universe theories suggest that under certain extreme conditions, one of these quantum fluctuations could have been so immense, so powerful, that it became stable and expanded into the universe we inhabit today. It effectively transforms the vacuum from an empty stage into a fertile ground, pregnant with the potential for reality, where the laws of physics themselves are the architects of creation. One of the most famous and influential proposals in this vein is the no-boundary proposal, developed by Stephen Hawking and James Hartle. This highly mathematical concept attempts to describe the initial state of the universe without invoking a problematic singularity or a divine intervention. Imagine going back in time towards the Big Bang. As you approach the beginning, space and time, according to the no-boundary proposal, become more like space than time, eventually curving around and smoothly closing off, much like the surface of a sphere. There's no sharp edge, no boundary, no singular point where time truly begins or where the laws of physics break down. Instead, the universe simply appears as a kind of self-contained, smooth, finite, and boundless entity in imaginary time that then transitions into the real time we experience. It's a universe that effectively has no beginning in the traditional sense, but rather smoothly emerges from a state where time itself is not well defined, allowing for a universe that is both self-contained and self-sufficient in its emergence. The no-boundary proposal beautifully illustrates the cosmic bootstrap idea. The universe simply is without needing an external cause. Its laws are not arbitrarily imposed but are, in some sense, self-consistent, allowing for its own spontaneous emergence. This means that the universe's existence is not a miracle, but a natural consequence of the fundamental laws of quantum physics and gravity. If the universe's initial conditions are described by this no-boundary state, then its statistical likelihood of existing becomes a calculable concept, stemming from the very fabric of spacetime itself. It bypasses the need for a before the Big Bang because the concept of time, as we understand it, becomes intertwined with the universe's very geometry, emerging alongside it rather than preceding it. This perspective deeply challenges our common-sense notions of time and causality, suggesting that the universe's beginning is not a singular point in time, but a state from which time itself emerges. Another aspect of the self-creating universe delves into the idea that the physical laws themselves are not just arbitrary rules, but are inherently interconnected and self-consistent, almost bootstrapping each other into existence. Some theories propose that the universe's existence and the specific values of its fundamental constants are not accidental but are precisely those that allow for its own emergence through quantum processes. This implies a profound circularity. The universe exists because its laws permit it, and its laws exist because the universe embodies them. It's a closed loop of self-consistency, where the very act of existing reinforces the conditions for existence. This level of self-organization from what appears to be chaos is a strong theme in these theories, positing that complex structures and order can spontaneously arise from fundamental principles without external input. However, the self-creating universe theories, especially concepts like the no-boundary proposal, are notoriously difficult to test directly. They rely on advanced concepts in quantum gravity, a field where a complete and unified theory remains elusive. The mathematical intricacies are immense, and interpreting the imaginary time of the no-boundary proposal into our real-time physics is a constant source of debate. Furthermore, the statistical likelihood of such a massive quantum fluctuation spontaneously occurring and leading to a universe like ours is incredibly small, leading some critics to question its plausibility. Even if these theories offer a compelling conceptual framework for a universe that is its own cause, the precise mechanism of such a spontaneous self-creation remains deeply theoretical and beyond our current observational reach. Nevertheless, the idea of a universe that bootstraps itself into existence, arising from the inherent potential of the quantum vacuum and the self-consistent nature of its own laws, remains one of the most intellectually stimulating and profound answers to the ultimate question of cosmic origins, pushing the very limits of what we consider to be nothing and the source of everything. While the self-creating universe theories explore how our cosmos might have bootstrapped itself from fundamental quantum principles, our next controversial idea flips our perspective entirely, proposing a truly mind-bending possibility: the universe as a black hole interior. Imagine for a moment that our entire cosmos, every star, every galaxy, every vast expanse of space-time, and even ourselves, is not simply existing in the vastness of an open, expanding universe. Instead, what if our entire reality is actually tucked away, contained within the event horizon of a gigantic black hole, which itself exists within a larger, parent universe? This isn't just a peculiar thought experiment. It's a theory that attempts to resolve some of cosmology's most perplexing puzzles by blurring the lines between creation and destruction, suggesting that the most powerful engines of cosmic collapse might also be the unexpected cradles of new realities. This audacious concept draws inspiration from the peculiar properties of black holes and the mathematics of cosmology. For an observer inside a black hole's event horizon, the future inevitably leads to the central singularity. Yet, from an external perspective in the parent universe, the black hole merely appears as a region of immense gravity from which nothing, not even light, can escape. The startling twist in this theory is that the physics inside a black hole, particularly near its singularity, can bear a striking resemblance to the conditions of the Big Bang. The intense gravitational compression and the rapid expansion of space within the black hole's interior, as predicted by some solutions to Einstein's equations, could very well mimic the early universe's expansion from an incredibly dense state. Therefore, what we experience as the Big Bang, the fiery, explosive beginning of our universe's expansion, could simply be the perspective of an internal observer, born within the confines of a black hole, looking outward into their expanding reality. One of the most compelling aspects of the black hole universe theory is its elegant solution to the Big Bang singularity problem. In the standard cosmological model, the universe sprang from an infinitely dense point, a singularity where the laws of physics break down. This is a difficult concept to reconcile with physical reality. However, if our universe were born inside a black hole, the singularity that forms at the black hole's center in the wider parent universe would be an event that our universe's inhabitants would never encounter as a beginning. Instead, the Big Bang would be seen as the ultimate expansion that resulted from the material from the parent universe crossing the event horizon and forming a new, expanding reality within. The singularity, in this view, is a feature of the parent universe, not a point of infinite density within our own. This allows for a continuous, albeit highly warped, space-time, avoiding the mathematical pitfalls of an absolute beginning from nothingness. Furthermore, this model offers a unique perspective on the cosmic fine-tuning problem, which often asks why our universe's physical constants are so perfectly calibrated for the existence of life. If universes can be formed inside black holes, and if different black holes in a parent universe might have slightly different characteristics or form from different initial conditions, then it implies a kind of natural selection. Black holes that happen to form universes with stable physical constants, allowing for long-lived stars and the development of complexity, would effectively be successful in giving rise to observers like us. This is a form of the anthropic principle, but situated within a concrete physical mechanism. It suggests that our universe's life-friendly properties are not a cosmic fluke, but a consequence of the conditions inside a particular type of black hole that allowed for its long-term evolution and the eventual emergence of conscious beings to ponder their origins. While intriguing, the black hole universe theory faces immense challenges. The greatest hurdle is the profound difficulty, if not impossibility, of any direct observation or communication with the parent universe. By definition, our universe would be causally isolated within the event horizon of its parent black hole, meaning no information or signal from the external universe could ever reach us. This makes the theory incredibly difficult to test empirically, prompting questions about its scientific falsifiability. How could we, from within, ever detect the boundaries of the black hole that contains us? What would be the telltale signs of our existence within such a structure? While mathematical modeling can explore the theoretical consistency of such a scenario, confirming it observationally remains a monumental, if not insurmountable, task. Despite these hurdles, the concept continues to be explored in theoretical physics, often as a way to unify seemingly disparate phenomena or resolve long-standing paradoxes. For example, some variations of the theory attempt to connect the expansion of our universe to the properties of growing black holes, suggesting a deep, almost symbiotic relationship between our cosmic destiny and the life cycle of these gravitational behemoths. Others explore how the specific conditions of a black hole's interior might naturally generate the initial density fluctuations observed in the cosmic microwave background, which seed the formation of galaxies. It encourages us to consider that the very act of collapse, the ultimate end for matter falling into a black hole, might paradoxically be the ultimate act of creation, giving birth to a new, expanding cosmos within its confines. It forces us to reconsider the fundamental distinction between creation and destruction, suggesting they are two sides of the same cosmic coin, where the swallowing of one reality gives rise to the explosive birth of another. While the black hole universe theory offers a nested cosmic reality, our next controversial idea flips our fundamental understanding of cosmic origins on its head, delving into the very nature of order and disorder, the entropy-driven universe. Imagine for a moment that the Big Bang, the fiery birth of our cosmos, wasn't a miraculous anomaly of incredibly low entropy, a state of perfect order that somehow gave rise to everything. What if instead the universe's origin is directly linked to the relentless, universal march towards increasing disorder? This provocative theory suggests that the Big Bang was not just an explosion, but a fundamental phase transition, a spontaneous rearrangement driven by the universe's inherent drive to maximize its entropy. This challenges the conventional wisdom that links the universe's beginning to an extreme state of low entropy, pushing us to consider a universe born from a paradoxical dance between chaos and emergent structure. The standard cosmological model posits that the universe began in an incredibly ordered, low-entropy state. Think of it like a perfectly organized deck of cards. As the universe expands, evolves, and structures form, entropy disorder inevitably increases, becoming a shuffled deck. This relentless increase in entropy is often called the second law of thermodynamics, effectively defining the arrow of time flows from order to disorder. The mystery then becomes, why did the universe start in such an incredibly low entropy state to begin with? This initial cosmic order is often considered a profound fine-tuning problem, demanding an explanation. However, the entropy-driven universe theory offers a radical alternative. What if the universe began in a state that, from a different perspective, was already tending towards higher entropy, or that the Big Bang itself was a process of entropy maximization? This often involves a reinterpretation of what entropy means at the quantum gravitational scale. Perhaps the initial state of the universe before the Big Bang was not empty but a highly energetic quantum foam-like state that was maximally disordered in some fundamental sense. The Big Bang, then, might not be a singular point from which order sprang, but a transition out of this chaotic, high-entropy primordial soup. Instead of beginning small and ordered, the universe began in a way that rapidly increased its effective volume and degrees of freedom, which inherently maximizes entropy. Imagine a system that, to achieve its highest possible state of disorder, must necessarily expand and allow for increasing configurations of its components. From this perspective, the Big Bang isn't a magical creation of order, but the most efficient way for an immensely energetic primordial state to transition into a more disordered, expanding configuration of spacetime and matter. One particularly fascinating aspect of this theory is how it attempts to reconcile the seemingly contradictory emergence of complex structures, like stars, galaxies, and even life itself, from a universe supposedly driven towards disorder. Here, the idea is that while total entropy always increases, local pockets of order can spontaneously arise. Think of a swirling eddy in a chaotic river. The river as a whole increases in disorder, but within that localized eddy, temporary, complex patterns emerge. The universe, in this view, is like a massive, self-organizing system. Its overall drive towards maximum entropy creates conditions where, paradoxically, gravitational instabilities can lead to the formation of stars and galaxies, which are highly ordered structures. These structures represent local decreases in entropy, but they do so by radiating heat and light into space, contributing to the overall, much larger, increase in the universe's total entropy. It's a cosmic trade-off, order here for disorder everywhere else. This thermodynamic approach to cosmic evolution challenges the very notion of the arrow of time. If the universe simply seeks to maximize entropy, and if the Big Bang was a manifestation of this drive, then perhaps the fundamental direction of time is intrinsically linked to this entropic gradient. We experience time flowing forward because that is the direction in which entropy increases. If a universe could somehow spontaneously decrease its entropy, time might even effectively reverse for it. The theory suggests that the very existence of our universe and its expansion is the most efficient path for entropy to increase from some initial, extremely energetic, and perhaps already maximally disordered quantum gravitational state. This implies that the Big Bang wasn't a unique, improbable event, but a thermodynamically inevitable outcome, a cosmic imperative driven by the laws of thermodynamics rather than merely governed by them. However, the entropy-driven universe theory faces immense conceptual and mathematical hurdles. Defining and quantifying entropy at the Planck scale, where gravity and quantum mechanics merge, is still an unsolved problem in physics. What exactly constitutes disorder in the earliest moments of spacetime? How does this initial high entropy state transition into the Big Bang expansion? And what are the precise mechanisms that allow for the subsequent formation of cosmic structures? Moreover, reconciling this perspective with the observed low entropy of the early universe, as evidenced by the smooth cosmic microwave background, requires sophisticated theoretical frameworks that are still under development. Nevertheless, by challenging the deeply ingrained assumption of a low entropy Big Bang, this theory forces us to reconsider the fundamental drivers of cosmic evolution. It prompts us to imagine a universe whose very birth was a consequence of its relentless pursuit of maximum disorder, paradoxically leading to the emergence of the complex order we observe around us, in a grand cosmic dance of creation and destruction driven by the ultimate thermodynamic imperative. While the entropy-driven universe suggests a cosmic imperative towards disorder, our next controversial idea offers a radically different perspective on the very nature of gravity, and by extension, the universe's origin, the Big Whoosh, or the theory of gravity as a fluid. Imagine for a moment that gravity isn't merely a static curvature of spacetime, as Albert Einstein brilliantly described it. What if instead it behaves more like a dynamic fluid, a cosmic ether, or an emergent phenomenon born from the collective behavior of something even more fundamental? This less conventional but deeply intriguing theory explores models where the universe's expansion, and indeed its entire structure, is driven by the flow and pressure within this hypothetical gravitational fluid, leading to a profoundly different origin scenario than the singular Big Bang. It challenges the very foundation of our understanding of gravity, suggesting it's not a fundamental force in the usual sense, but something that arises from deeper, fluid-like dynamics. The concept of gravity as a fluid emerges from attempts to bridge the gap between general relativity and quantum mechanics. While general relativity beautifully describes gravity on large cosmic scales, it struggles to integrate with quantum mechanics at the very small subatomic levels. Theoretical physicists have long sought a quantum theory of gravity. One approach explored by some researchers is to consider gravity not as a fundamental force mediated by a hypothetical graviton particle, but as an emergent property, much like temperature or pressure emerges from the collective motion of countless individual atoms. In this fluid gravity paradigm, spacetime itself is not a fixed, passive background but a dynamic medium, a kind of gravitational superfluid that can flow, ripple, and exert pressure. The Big Whoosh, then, would be the initial rapid expansion of this cosmic fluid, a wave of gravitational energy causing the universe to inflate and expand, rather than an explosion from an infinitely dense point. One of the most compelling aspects of the gravity as a fluid theory is its potential to offer alternative explanations for some of cosmology's most stubborn mysteries, particularly dark energy and the universe's early evolution, potentially alleviating the need for cosmic inflation or dark matter by reinterpreting gravity's role. In the standard model, dark energy is a mysterious, unseen force causing the universe's accelerated expansion. If gravity behaves like a fluid, then the universe's expansion might be driven by the inherent pressure or tension within this gravitational fluid itself. The accelerated expansion we observe wouldn't be due to a new, exotic form of energy, but rather a natural consequence of the fluid dynamics of spacetime. Imagine a fluid under certain conditions capable of generating its own expansive pressure, pushing the fabric of spacetime apart from within. This elegant reinterpretation could eliminate the need for a separate dark energy component, making the universe's energy budget much simpler and more unified. Furthermore, this fluid interpretation of gravity could also provide an alternative mechanism for the early universe's rapid expansion, often attributed to cosmic inflation. Instead of a hypothetical, inflated field driving the early universe's exponential growth, the Big Whoosh model suggests that the inherent properties of the gravitational fluid itself could naturally lead to a period of rapid expansion. Perhaps the very creation or initial perturbation of this fluid created a wave of expansion that stretched the universe to immense scales, smoothing out initial inhomogeneities and leading to the flat, uniform universe we observe today. This would be a more intrinsic, self-generating form of expansion, arising directly from the fundamental nature of spacetime as a fluid. It bypasses the need for an additional, temporary field, offering a more parsimonious explanation for the very early universe's behavior. The implications for dark matter are also intriguing. If gravity is an emergent phenomenon, its behavior might differ slightly at various scales or under different conditions than predicted by standard general relativity. Some fluid gravity models explore how inhomogeneities or turbulence within this gravitational fluid could mimic the effects currently attributed to dark matter. Instead of requiring vast halos of invisible particles gravitationally pulling galaxies together, perhaps these gravitational fluid dynamics could explain the anomalous rotation curves of galaxies or the gravitational lensing observed in galaxy clusters. This would mean that the missing mass isn't missing at all, but rather is a manifestation of the complex, fluid-like behavior of gravity itself, an unseen current or pressure within the cosmic sea. However, the gravity as a fluid theory represents a radical departure from mainstream physics and faces significant theoretical and observational challenges. The mathematical framework for describing gravity as an emergent fluid is still under development, and rigorously deriving all the observed properties of gravity and the universe from such a model is an enormous task. Moreover, proving that gravity actually behaves as a fluid rather than a fundamental force would require new experimental and observational techniques capable of probing the very nature of spacetime at its most fundamental level. Visualizing fluid dynamics simulations applied to cosmology can offer intuitive insights, showing how flows and pressures might drive cosmic evolution, but these remain conceptual models needing empirical validation. This highly speculative theory challenges us to fundamentally rethink gravity itself, hinting at a universe born not from a point, but a powerful, cosmic wave of fluid-like gravity that continues to shape reality. While the idea of gravity as a fluid offers a dynamic, flowing origin for our cosmos, our next controversial theory takes us back in time, to an idea far more ancient and intuitive, yet surprisingly resonant with modern concepts, the cosmic egg or the primordial atom. Imagine for a moment not a vast expanse of empty space, but the entire universe compressed into an unimaginably dense, hot, singular egg or atom from which everything burst forth. This concept, while largely superseded by contemporary scientific models, holds profound historical significance, representing humanity's earliest attempts to grapple with the mystery of creation and offering an almost poetic precursor to our modern understanding of the Big Bang. It's a bridge between ancient myth and nascent science, illustrating a deep-seated human intuition about a singular, explosive beginning. The notion of a cosmic egg isn't confined to a single culture or era. It's a concept that appears in various forms across countless ancient myths and philosophical traditions worldwide. From the Orphic egg in ancient Greece, from which the primordial deity Phanes hatched, to the Hiranyagarbha, or golden embryo in Hindu cosmology, to the Pangu egg in Chinese mythology, which contained chaos before splitting into heaven and earth, these narratives consistently depict creation emerging from a contained, often spherical, and highly potent initial state. These myths were not scientific theories in our modern sense, but profound attempts to explain the universe's apparent order and diversity from a primordial unity. They speak to a universal human desire to trace everything back to a single source, a single point of origin where all potential was contained before its grand unfolding. The resonance of such myths across diverse cultures suggests a shared human intuition about the universe's beginnings, a deep-seated recognition that complexity often arises from simplicity. What makes the cosmic egg concept particularly intriguing in the context of our discussion of controversial origin theories is its striking conceptual similarity to the scientific idea of a pre-Big Bang singularity. While the ancient concept was born from intuition and observation of life cycles, an egg hatching into a complex organism, and the modern singularity from mathematical extrapolation of general relativity, both describe an initial state of unimaginable density and compression from which the universe expanded. Georges Lemaitre, the Belgian priest and physicist who first proposed what would later be called the Big Bang theory, actually referred to this initial state as the primeval atom. He envisioned the entire universe compressed into a single quantum, unstable and poised to explode, releasing all the matter and energy that would eventually form galaxies, stars, and planets. This intellectual leap from an ancient mythical egg to a scientific primordial atom demonstrates how deeply ingrained the idea of a singular, highly compressed origin point is in the human psyche, whether approached through myth, philosophy, or theoretical physics. However, despite these fascinating conceptual parallels, it's crucial to understand that the cosmic egg or primordial atom, as conceived historically, lacks the empirical backing and predictive power of modern cosmological models. It was a qualitative idea, not a quantitative one. It didn't make testable predictions about cosmic expansion, the abundance of elements, or the existence of a cosmic microwave background. Modern cosmology, particularly the Big Bang theory, built upon these early intuitions but rigorously tested them against observational data, refining them with mathematics and physics. The discovery of cosmic expansion, Hubble's law, and the cosmic microwave background radiation, Penzias and Wilson, provided the crucial empirical evidence that elevated the Big Bang from speculation to the leading scientific model. These discoveries allowed cosmologists to calculate the universe's age, predict the formation of light elements, and trace the universe's evolution in exquisite detail. Yet, even though the cosmic egg has been superseded scientifically, its symbolic power and its echoes in modern cosmology underscore a fundamental philosophical challenge. What exactly was this egg? What lay outside it? What caused it to hatch or explode? Modern physics still grapples with the singularity problem, the infinitely dense point at the very beginning of the Big Bang where known laws of physics break down. In a way, the cosmic egg concept, in its simplicity, confronts this mystery head-on. It posits a singular beginning, but then leaves the ultimate cause within the realm of the unknown or the mythical. It forces us to acknowledge that even our most advanced scientific theories still contain elements that push the boundaries of our understanding, where the language of mathematics sometimes converges with the almost mystical implications of creation from a preceding state of ultimate compression. The cosmic egg, therefore, serves as a powerful reminder of humanity's enduring quest to comprehend its cosmic beginnings, a quest that began in ancient myths and continues to inspire cutting-edge scientific inquiry. While the cosmic egg provides a fascinating historical echo of a singular beginning, our journey now takes us back into the cutting-edge, speculative realm of theoretical physics, exploring an idea that completely reframes the moment of creation, the pre-Big Bang string theory. Imagine for a moment that our universe, with all its galaxies and stars, didn't just burst into existence from an infinitely dense point. What if instead it evolved from an incredibly long, cold, and static precursor state, a universe that existed in a radically different form before undergoing a violent yet continuous transition that ignited the Big Bang as we know it? This groundbreaking theory, deeply embedded in the complex framework of string theory, endeavors to eliminate the problematic Big Bang singularity entirely, offering a smooth, continuous evolutionary path through the very earliest moments of cosmic history. At its heart, the pre-Big Bang string theory posits that our current hot, expanding universe is merely one phase in a much longer cosmic saga. Picture an initial, almost infinitely distant past where the universe was incredibly cold, nearly empty, and perhaps contracting ever so slowly or even static. In this scenario, gravity was extremely weak, and the universe existed in a state dominated by a specific configuration of strings, those fundamental, one-dimensional vibrating filaments that string theory proposes are the ultimate building blocks of reality. As this primordial state evolved, driven by subtle interactions between these strings and perhaps exotic higher dimensional fields, gravity would have begun to strengthen dramatically. This strengthening of gravity would have led to a period of rapid contraction, causing the universe to become hotter and denser, culminating not in a mathematical singularity, but in a bounce or a turnaround event. This turnaround point, where the universe transitions from contracting to expanding, is what we perceive and call the Big Bang. Thus, the Big Bang isn't a singular creation event. It's a phase transition, a moment of cosmic rebirth from a previously existing, albeit exotic, state. This theory offers a particularly elegant solution to the Big Bang's troublesome singularity. In standard cosmology, the singularity is a point where our current laws of physics break down, making it impossible to describe what happened at the very beginning. The pre-Big Bang model effectively pushes this problematic point into the infinite past, or rather, it replaces it with a continuous, albeit dramatic, process. It argues that because string theory provides a framework where gravity becomes fundamentally quantum at extremely high energies and curvatures, it naturally smooths out any potential singularities. The universe never actually reaches infinite density. Instead, the stringy nature of reality, with its higher dimensions and fundamental string length, imposes a minimum physical scale. When the universe contracts to this incredibly small, dense state, it doesn't collapse to a point, but rather undergoes a quantum bounce or simply transitions into an expanding phase, all within the consistent rules of string theory. This ensures that the entire cosmic evolution, from the pre-Big Bang state through to today, is governed by a single, unified set of physical laws. Furthermore, the pre-Big Bang string theory attempts to explain cosmic inflation, the rapid, exponential expansion that the standard model invokes to smooth out the universe and explain its initial uniformity. In this string-based model, the conditions that lead to inflation might be an intrinsic part of the transition from the contracting, cold phase to the expanding, hot phase. The intense energies and curvatures near the bounce point could naturally give rise to a period of rapid expansion, or an inflationary era, which then sets the stage for the subsequent evolution of the universe we observe. This means that inflation isn't an ad hoc addition, but an organic consequence of the string-theoretic dynamics governing the transition. This framework suggests that the very properties of our universe, its flatness, homogeneity, and the specific spectrum of primordial fluctuations that seeded galaxy formation are not just random initial conditions, but direct relics of this pre-Big Bang history and the violent turnaround that occurred. The theory also makes use of string theory's higher dimensions and branes to describe this exotic cosmic history. Our four-dimensional spacetime, three spatial dimensions plus time, might be just one brane embedded in a larger, higher-dimensional space. The interaction and dynamics of these branes, or the way the universe contracts and expands within these higher dimensions, could be crucial to the pre-Big Bang scenario. For example, the very strength of gravity in our universe might be determined by the size and shape of these extra dimensions, which could evolve over cosmic time. The turnaround might involve complex dynamics within these hidden dimensions, fundamentally reshaping the local spacetime we perceive as our universe. This means that the history of our universe is not just a story of expansion in four dimensions, but an intricate dance within a much larger, multi-dimensional stage, where the properties of our visible reality are influenced by the unseen realm of stringy interactions. However, like many theories at the forefront of fundamental physics, the pre-Big Bang string theory faces immense challenges. String theory itself is still a work in progress without definitive experimental verification, and the specific details of a pre-Big Bang phase are highly mathematical and difficult to connect to direct observations. Proving that such a cold, static phase existed, or that a bounce occurred due to stringy physics, would require incredibly precise measurements of the cosmic microwave background or gravitational waves that could carry imprints from such an early, high-energy era. Such signals would be incredibly faint and complex to distinguish from other cosmological phenomena. Nevertheless, the pre-Big Bang string theory offers a compelling, singularity-free vision of cosmic origins, daring to describe a universe that had a long, slow existence before its fiery birth, a universe whose beginning was not an explosion from nothing, but a dramatic transition from an even stranger, string-dominated past. It suggests that our current cosmic epoch is but one chapter in an infinitely greater and far more complex cosmic novel, continually evolving through different phases. While the pre-Big Bang string theory offers a long, slow cosmic evolution, our next controversial idea abandons purely physical explanations entirely, proposing a truly mind-bending possibility, the conscious universe or the participatory anthropic principle. Imagine for a moment that our universe, with all its stars, galaxies, and even its fundamental laws, is not merely out there, existing independently of any observer. What if, instead, consciousness is not just a byproduct of the universe, but an integral, perhaps even foundational, element of its very existence and origin? This highly philosophical and deeply controversial concept suggests that the universe could not exist in a definite, fully realized state until it was observed or participated in by conscious beings, implying a co-creative role for awareness itself. It blurs the lines between physics, philosophy, and even spirituality, challenging deeply ingrained materialist views of the cosmos. This audacious theory stems directly from the most puzzling aspects of quantum mechanics, the very framework that describes reality at its smallest scales. In quantum experiments, particles like electrons or photons behave like waves, existing in a superposition of all possible states simultaneously until they are observed or measured. At that point, the wave function collapses and the particle chooses a single, definite state. This observer effect is one of the most unsettling and fundamental mysteries of quantum physics. The participatory anthropic principle, most famously articulated by physicist John Wheeler, takes this idea to its extreme cosmological conclusion. Wheeler proposed that the universe literally comes into being and takes on specific characteristics through the act of observation. He famously stated, "The universe is a self-excited circuit. It exists because we observe it." This implies a profound, almost symbiotic relationship between the universe and consciousness. It suggests that the cosmos and life are inextricably linked, each incomplete without the other. The universe provides the stage for consciousness, and consciousness, in turn, brings the universe into definite existence. This theory effectively turns our everyday understanding of reality on its head. We typically assume that the universe existed first, then life evolved, and finally, consciousness emerged as a complex product of biological brain. The participatory anthropic principle suggests a reversed or interwoven causality. It posits that the universe, during its early, quantum-dominated stages, existed only in a probabilistic, indeterminate state, a vast quantum superposition of all possible universes. It was only with the eventual emergence of conscious observers, us, or perhaps other forms of awareness across cosmic time, that the universe snapped into being, crystallizing into the specific reality we perceive. Our consciousness, in this view, is not just passively observing an objective reality but actively participating in its manifestation. This doesn't mean that an individual thought creates a star, but rather that the very existence of a universe of stars required the eventual presence of some form of awareness to collapse its cosmic wave function. One of the most powerful implications of this theory is its potential to explain the fine-tuning puzzle. As we've discussed, the physical constants of our universe seem miraculously calibrated for the existence of life. If they were even slightly different, stars wouldn't form or atoms wouldn't be stable. The participatory anthropic principle offers a radical, almost tautological solution. The universe is fine-tuned for life because it is life or consciousness that brought it into definitive existence. We observe a universe conducive to life because any universe not conducive to life would not have produced conscious observers to collapse its wave function into a definite reality. This elegantly bypasses the need for an external designer or an infinite number of parallel universes. Our universe is simply the one that was observed into being. It is the path that was chosen out of a multitude of quantum possibilities by the eventual emergence of consciousness. This theory profoundly challenges the materialist worldview, which asserts that matter and energy are fundamental, and consciousness is merely an emergent property of complex physical systems. The conscious universe posits that consciousness, or something akin to it, might be a fundamental property of reality, perhaps even more fundamental than matter or energy. It suggests that the cosmos is not just a collection of inert particles, but an interconnected, living system where awareness plays a crucial, active role. This opens up philosophical avenues for exploring the nature of mind, the spiritual implications of existence, and the ultimate purpose of the universe. If consciousness is essential for the universe to be real, then our existence is not just accidental but deeply purposeful, woven into the very fabric of space-time from its inception. However, the conscious universe theory faces immense scientific and philosophical criticisms. Many physicists argue that the observer effect in quantum mechanics does not require consciousness, but simply an interaction with a measuring device. A particle interacting with a sensor is sufficient to cause wave function collapse. It doesn't need to be observed by a sentient being. Critics also point to the difficulty of defining consciousness in a way that is scientifically testable and verifiable. How far back in time did consciousness need to exist to collapse the early universe? Did the first single-celled organisms have enough consciousness to bring the universe into being? And what does it mean for a universe to exist in an indeterminate state before observation? These are profound, almost unanswerable questions within our current scientific framework. Despite these challenges, the participatory anthropic principle forces us to confront the deepest implications of quantum mechanics and the role of consciousness in shaping reality. It asks us to consider a universe that is not merely observed by conscious beings, but perhaps fundamentally, intrinsically, a conscious entity itself in some profound and mysterious way. While the conscious universe delves into the mind's role in shaping reality, our next controversial idea offers a profoundly different, almost constantly repeating view of cosmic creation, not as a singular event but as an ongoing, infinite process, the universe as a fractal. Imagine for a moment that the cosmos isn't just vast beyond comprehension, but also infinitely complex and remarkably self-similar, mirroring intricate patterns at every conceivable scale, from the smallest quantum particles to the largest cosmic structures. This theory, more a philosophical framework and a mathematical lens than a singular physical model, suggests that the universe's origin might be understood not through a linear timeline leading to a beginning, but rather as a continuous unfolding of these self-similar patterns. We'll explore how fractal geometry, with its mesmerizing beauty and recursive nature, could offer a radically different way to interpret cosmic structure, evolution, and perhaps even its lack of a distinct origin. It suggests a cosmos that is infinitely deep, perpetually revealing new layers of detail, regardless of how closely or broadly you examine it, much like a mathematical fractal. At its core, fractal geometry is the study of shapes that exhibit self-similarity, meaning they look roughly the same at all levels of magnification. Think of a snowflake. Each arm of the snowflake is a smaller version of the whole, and each tiny branch on that arm is a smaller version still. Or consider a fern, where each frond is a miniature replica of the entire plant. Nature is replete with fractals, from coastlines and mountain ranges to river networks and the branching patterns of trees and blood vessels. The universe as a fractal theory posits that this fundamental principle of self-similarity extends to the largest and smallest scales of the cosmos. It suggests that the distribution of galaxies and galaxy clusters forming a vast cosmic web might exhibit fractal properties. Even the very fabric of space-time at its most fundamental level, or the organization of quantum particles, could potentially follow fractal rules. If the universe is indeed a fractal, it implies a deep, underlying order to what often appears as cosmic randomness, hinting at a universe that is both endlessly complex and harmoniously repetitive. One of the most intriguing aspects of this concept is how it challenges the traditional notion of a singular, distinct origin point for the universe. If the universe is a fractal, then perhaps it has no true beginning or end in the conventional sense, but rather a continuous process of self-organization and unfolding across scales. A fractal doesn't start from a point and build up, it simply is, defined by its recursive rules. Similarly, a fractal universe might not have begun at the Big Bang, but rather the Big Bang itself could be understood as a particular manifestation of a universal fractal process, a moment of transition within an endlessly self-replicating cosmic structure. This means the question shifts from what was before the Big Bang to what are the recursive rules that generate the universe at every scale? It suggests that what we perceive as the birth of our universe is merely one iteration in an infinite sequence of self-similar events, always creating new detail and complexity, but always governed by the same underlying fractal logic. The implications for cosmic structure are profound. When astronomers map the distribution of galaxies in the universe, they often find that matter isn't uniformly distributed but clumps together in vast filaments, superclusters, and voids, forming a network often called the cosmic web. Some studies have suggested that this cosmic web exhibits fractal properties, at least within certain observational limits. This means that if you zoom in on a small section of the web, the patterns of galaxy distribution might resemble the patterns of galaxy clusters on larger scales, and so on. If this fractal scaling holds true for the entire universe, it would mean that the universe is not homogeneous at all scales, but rather, its non-uniformity is a fundamental, self-repeating pattern. This would challenge the cosmological principle, which states that the universe is homogeneous and isotropic, the same in all directions on large scales, a cornerstone of the standard Big Bang model. A truly fractal universe would be hierarchically structured with infinite detail, without reaching a point of ultimate smoothness. Furthermore, the concept of a fractal universe can extend to the very small, to the realm of quantum mechanics. Some highly speculative theories propose that the fabric of spacetime itself at the Planck scale might possess a fractal dimension rather than being smooth and four-dimensional. This could provide a novel way to bridge the gap between general relativity and quantum mechanics. If spacetime itself is a fractal, then the irregularities and quantum fluctuations that plague our understanding of the early universe might be inherent properties of a fractal geometry with its infinite detail and self-intersections. This could mean that the Big Bang was not a unique event where spacetime burst forth from nothing, but a phase transition within an already existing fractal spacetime, where the fractal dimension of the universe changed, leading to the emergence of the smooth, expanding spacetime we experience today. However, the universe as a fractal theory, while conceptually rich, faces significant challenges and remains largely on the philosophical edge of cosmology, rather than a mainstream scientific model. Quantifying and proving true fractal behavior at all cosmic scales with observational data is incredibly difficult, as observational biases and limitations can mimic fractal patterns. Furthermore, the concept struggles to provide concrete, testable predictions about specific cosmic phenomena, such as the cosmic microwave background or the abundance of light elements, which the standard Big Bang model explains so well. While intriguing, it lacks the detailed mathematical framework and empirical support that would elevate it to a fully fledged, testable scientific theory of origin. Nevertheless, the idea of a fractal universe offers a compelling, almost artistic, alternative to the linear narrative of cosmic creation, forcing us to consider a cosmos that is infinitely recursive, constantly generating new levels of complexity and detail, and perhaps never truly beginning but always unfolding in a timeless, self-similar dance. While the universe as a fractal suggests an infinitely recursive cosmos, our next controversial theory delves into the most fundamental question of all: can the universe literally create itself from nothing? This is the renowned and often hotly debated argument put forth by physicist Lawrence Krauss in his influential work, A Universe from Nothing. Krauss famously contends that the universe could indeed have arisen from nothing, but it's crucial to understand his very specific definition of that loaded word. He is not referring to an absolute philosophical void, a state of non-existence so complete that it lacks even the laws of physics. Instead, he speaks of a nothing that is inherently brimming with potential, a dynamic arena where fundamental rules allow for spontaneous genesis. This challenges our intuitive, everyday understanding of creation and pushes the boundaries of what we conceive as a cosmic starting point. It's an intellectual tightrope walk, navigating between scientific definitions and philosophical expectations, ultimately arguing that the universe's origin is not an uncaused miracle, but a natural consequence of the laws of quantum mechanics. At the heart of Krauss's argument lies the baffling, yet empirically verified, reality of the quantum vacuum. In classical physics, a vacuum is simply empty space, devoid of matter or energy. But in the strange and wonderful world of quantum mechanics, a true vacuum is far from empty. It's a seething, effervescent foam of activity, a vibrant sea of potential energy. Here, the Heisenberg uncertainty principle dictates that particles and antiparticles can constantly pop into and out of existence for fleeting moments, borrowing energy from the vacuum before annihilating each other and vanishing again. These are virtual particles, existing just long enough to have a measurable effect on reality. Krauss argues that this nothing, this dynamic quantum vacuum, is the ultimate breeding ground for everything. It's not a static void, but a fertile arena governed by the laws of quantum field theory, capable of spontaneously generating matter, energy, and even space-time itself. The universe, in this view, didn't come from absolute nothingness, but from a state where the fundamental laws of physics were already in play, defining this quantum nothingness and giving it the inherent potential for creation. Building on this, Cross posits that if the laws of quantum mechanics allow for matter and energy to spontaneously appear from the vacuum, then there's no reason why an entire universe couldn't do the same. Imagine a quantum fluctuation so incredibly vast, so immensely powerful, that it didn't just produce a pair of particles, but the very fabric of space-time, along with all the matter and energy within it. The total energy of the universe, Cross often points out, could in fact be zero. If the positive energy of matter and radiation is precisely balanced by the negative gravitational potential energy, the energy required to pull everything apart, then the universe could theoretically have emerged from nothing without violating the law of conservation of energy. It's like digging a hole. The whole negative energy is created at the expense of the dirt piled up next to it positive energy, resulting in a net energy change of zero. In this scenario, the universe is the ultimate free lunch, arising naturally from the quantum vacuum without needing an external input or a pre-existing cause, essentially allowing the universe to bootstrap itself into existence from this very specific type of nothing. One of the most powerful aspects of Cross's argument is its ability to circumvent traditional philosophical and theological objections to creation ex nihilo, creation from absolute nothing. Philosophers often argue that from nothing, nothing comes, but Cross redefines nothing not as the absence of everything, but as a physically defined state governed by established laws. This sidesteps the need for a divine creator or an uncaused first cause, instead placing the origin squarely within the realm of scientific inquiry. He emphasizes that the laws of physics themselves are fundamental, and it is these laws operating on a quantum vacuum that provide the mechanism for spontaneous creation. The question then shifts from who created the universe to what are the fundamental laws that govern the quantum vacuum, allowing for the emergence of universes? This perspective makes the universe not a miraculous event, but a natural, albeit extremely rare, outcome of the inherent properties of reality described by quantum mechanics and general relativity. However, Cross's bold assertion, while compelling to many scientists, has not been without significant controversy and critique, particularly from philosophers and theologians. The primary contention revolves precisely around his definition of nothing. Critics argue that his nothing is not true philosophical nothingness, as it still presupposes the existence of quantum fields, laws of physics, and space-time. If these fundamental elements already exist, then the universe isn't truly coming from nothing in the traditional sense, but from a pre-existing, albeit empty, substratum. This distinction is crucial as it affects whether the theory truly addresses the ultimate origin question. Furthermore, while the concept of a zero-energy universe is appealing, its full implications and precise mechanics within a unified theory of quantum gravity are still matters of active research and speculation. Nevertheless, Cross's work has profoundly reshaped the popular and scientific discourse around cosmic origins, forcing us to think more deeply about the nature of nothing and the astonishing power of fundamental laws to bring forth existence itself. While Cross's universe from nothing suggests our cosmos arose from a quantum vacuum, our next controversial idea expands this concept exponentially, proposing a truly mind-bending origin story, the multiverse from quantum fluctuations. Imagine a cosmic foam not just generating our universe, but continuously bubbling forth an infinite array of universes, each potentially with its own unique laws of physics, its own dimensions, and its own destiny. This theory posits that the entire multiverse, a boundless collection of realities, could have spontaneously emerged from a pre-existing quantum foam or vacuum, where every possible universe, no matter how wild or strange, could simply pop into existence as a random yet inevitable quantum event. This takes the probabilistic nature of quantum mechanics to its ultimate cosmological conclusion, suggesting that reality is far vaster and more diverse than we could ever conceive. At the heart of this idea is the understanding of the quantum vacuum not as empty space, but as a sea of latent energy governed by the inherent uncertainties of quantum mechanics. Just as virtual particles constantly flicker into and out of existence in our local vacuum, this theory proposes that on a much grander cosmic scale, entire universes could similarly materialize. Imagine a vast primordial quantum foam, an ultimate ground state before anything we recognize as spacetime existed. Within this foam, ceaseless quantum fluctuations occur like tiny ripples on an infinite pond. Occasionally, one of these ripples might become stable enough, perhaps inflating rapidly, to detach and form its own self-contained bubble of spacetime, a new universe. Our universe, therefore, would be just one such bubble, one of countless outcomes in an endless cosmic lottery, a single realization from an infinite probability space. This transforms the origin question from "how did our universe begin?" to "how did this cosmic bubbling process generate such an incredible diversity of realities?" This concept ties directly into the theory of cosmic inflation, which, as we discussed earlier, proposes a period of hyper-rapid expansion in the very early universe. In many inflationary models, the process of inflation itself is eternal. That is, once inflation starts, it never truly stops everywhere. Instead, it continuously churns, spitting out new pocket universes as it proceeds. The multiverse from quantum fluctuations essentially provides the seed for this eternal inflation. The quantum foam generates the initial fluctuations, which then get stretched and expanded by inflation into full-fledged universes. This means that the universe we inhabit isn't unique, but rather an isolated island in an infinitely vast ocean of other realities, some expanding, some contracting, some with laws of physics unrecognizable to us. It suggests that the Big Bang wasn't a singular event of creation, but merely the localized emergence and rapid expansion of one particular quantum fluctuation, a bubble forming within an already existing, albeit abstract, meta-reality. The multiverse from quantum fluctuations offers a compelling, albeit unsettling, solution to the perplexing problem of cosmic fine-tuning. If there are an infinite number of universes, each generated by random quantum fluctuations, and each potentially having subtly or wildly different physical laws and constants, then it's no longer surprising that we find ourselves in a universe where conditions are just right for life. In such a vast cosmic landscape, every conceivable combination of physical laws and initial conditions would eventually manifest. We simply live in one of the universes that happens to have the precise values for gravity, electromagnetism, and nuclear forces that allow for the formation of stars, planets, and complex chemistry. Our existence isn't a miraculous coincidence, but merely a statistical inevitability within an infinite ensemble of possibilities. We are here not because our universe was specially designed for us, but because out of an infinite number of random rolls of the cosmic dice, one was bound to land on, life permitting. This theory also has profound implications for the origin of information itself. If every quantum fluctuation, every possible configuration of reality, can manifest as a universe, then the information content of the multiverse would be effectively infinite. Our universe, with its specific laws and initial conditions, represents a particular instantiation of this information. The question then becomes, where does this fundamental quantum foam and its inherent potential come from? Is it an irreducible, axiomatic ground state of reality, or does it, too, emerge from something even more fundamental? The theory implicitly suggests that the universe, and indeed the multiverse, is a self-organizing system where the rules of quantum mechanics inherently contain the blueprint for infinite cosmic diversity. It transforms creation from a singular event into an ongoing fractal process, a perpetual cosmic fountain of new realities. However, the multiverse from quantum fluctuations, like all multiverse theories, faces significant challenges regarding its testability and falsifiability. If these other universes are causally disconnected from our own, how can we ever hope to detect them or gather empirical evidence for their existence? The sheer unobservability of these other realities makes it difficult to move the theory from the realm of fascinating speculation to verifiable science. While the theory offers elegant solutions to the fine-tuning problem, many scientists argue that a theory that cannot be tested isn't truly scientific, or at least falls outside the traditional scientific method. Others worry about the measure problem, which asks how we assign probabilities to different outcomes or how we even define typical observers within an infinite multiverse. Despite these fundamental hurdles, the idea of a universe endlessly bubbling forth from the quantum foam remains a powerful intellectual framework, pushing the boundaries of what we understand about cosmic origins and forcing us to confront the possibility that our universe is just one tiny, fleeting expression within an unimaginably vast and diverse cosmic tapestry, constantly being woven. The inherent potential of the quantum realm. While the multiverse from quantum fluctuations offers a statistical explanation for why our universe exists, our next controversial theory delves into one of the deepest, most persistent puzzles in cosmology, often pushing the boundaries between science, philosophy, and even theology: the fine-tuning paradox and the argument for intelligent design. Imagine for a moment that the universe is like an incredibly complex machine, say, a finely tuned watch. Every gear, every spring, every tiny component has to be precisely the right size, shape, and tension for the watch to keep perfect time. Now, what if we discovered that the fundamental constants of our entire universe, the very laws that govern its existence, are calibrated with such astonishing precision that even a minuscule deviation would render it incapable of supporting life? This isn't just a happy coincidence according to this theory. It hints at an underlying purpose and intentional design. It posits that the universe is so incredibly hospitable to life that it implies an intelligent creator or designer. The scientific argument for fine-tuning centers on the observation that numerous physical constants and initial conditions of the universe appear to be precisely calibrated for the existence of complex life. Take, for instance, the strength of the strong nuclear force which binds protons and neutrons together in atomic nuclei. If it were even slightly weaker, stable atomic nuclei wouldn't form, meaning no atoms beyond hydrogen. If it were slightly stronger, hydrogen would burn too quickly, leading to a universe of only heavy elements incompatible with life as we know it. Similarly, consider the cosmological constant, the mysterious energy density of empty space currently driving the universe's accelerated expansion. Its observed value is incredibly tiny, almost infinitesimally close to zero. Yet if it were just a little larger, the universe would have expanded so rapidly that matter couldn't clump together to form stars and galaxies. If it were a little smaller, the universe might have collapsed back in on itself before life could emerge. It's a cosmic tightrope walk where our universe seems balanced on a razor's edge, seemingly designed for biological complexity. Another striking example of fine-tuning relates to the properties of water, the essential solvent for life. Water's unusual properties, like its ability to expand when it freezes allowing ice to float, and lakes to not freeze solid from the bottom up, and its high specific heat capacity which moderates global temperatures, are crucial for Earth's climate and the chemical reactions necessary for life. These properties are directly linked to the precise values of fundamental constants governing atomic interactions. The mass difference between a proton and a neutron, the precise value of the electron's charge, the expansion rate of the universe, the balance between gravity and electromagnetism. The list of these seemingly miraculous cosmic coincidences stretches on, each one a critical prerequisite for the universe to be life-permitting. The argument is that the probability of all these values randomly aligning to allow for life is so astronomically small that it defies credulity, pushing some to consider a non-random, intentional explanation. Of course, this theory is immensely controversial in scientific circles. Critics argue that attributing fine-tuning to an intelligent designer steps outside the realm of testable, falsifiable science and into the domain of metaphysics or theology. Science, by its nature, seeks natural explanations for natural phenomena. The invocation of a supernatural designer is seen by many as a God of the gaps argument, where divine intervention is posited to explain phenomena for which we currently lack a complete scientific explanation. As our understanding of physics deepens, many of these gaps are filled by natural processes. Furthermore, some argue that the fine-tuning argument suffers from a fallacy of probability. We are here, so of course, we observe a universe that is hospitable to us. It's like a puddle marveling at how perfectly the hole it fills fits its shape. One of the most potent scientific counter-arguments to the fine-tuning paradox comes from the multiverse theories we just discussed. If our universe is just one of an infinite number of universes, each with different physical laws and constants, then the apparent fine-tuning of our universe is no longer a miracle but a statistical inevitability. In this cosmic lottery, countless universes are unwinners, too unstable or too short-lived to produce life. But given an infinite number of tries, it becomes virtually guaranteed that a universe with the right conditions for life, like ours, would eventually emerge. We simply happen to find ourselves in one of the lucky few. This shifts the burden of proof from explaining a designer to explaining the mechanism that generates such a vast array of universes, such as eternal inflation or quantum fluctuations producing new realities. This remains a potent debate not just between science and philosophy, but within cosmology itself. For some, the fine-tuning is simply a brute fact, a boundary condition of our universe that we must accept until a deeper physical theory explains it. For others, it's a profound clue hinting at a reality far grander than our current understanding. Advocates of intelligent design frequently cite fine-tuning as compelling evidence for a divine creator, seeing it as the signature of a cosmic architect. Scientists, however, generally strive to find naturalistic explanations for all observed phenomena, even those as seemingly improbable as the fine-tuning of the universe. The debate over fine-tuning is a microcosm of the larger human quest for answers to ultimate origins, reflecting our deepest desires to understand why the universe exists and why it is capable of supporting us. It forces us to confront the limits of our knowledge and the inherent wonder embedded in the laws that govern everything. While the fine-tuning paradox delves into the remarkable precision of our universe's constants, our final controversial theory takes us into an entirely different realm, proposing that the universe's origin is tied not to material creation, but to abstract information, the universe as a computational construct. Imagine for a moment that the universe isn't fundamentally made of matter or energy, but of information encoded, processed, and manifested through a vast cosmic computation. This theory suggests that the complex fabric of reality, from the laws of physics to the particles that make up everything, could be viewed as the output of an incredibly sophisticated computational process. It challenges our deepest assumptions about what is truly fundamental, implying that at its core, the universe might be an algorithm, a grand machine executing code, or even a simulation designed for some unknown purpose. The roots of this idea lie in the growing recognition that information plays a surprisingly fundamental role in physics. From the information stored within a black hole's event horizon, as described by the holographic principle, to the quantum bits of information, qubits, that form the basis of quantum computing, physicists are increasingly finding that information is not merely a descriptor of reality, but perhaps a constituent element of it. The it-from-bit philosophy, championed by physicist John Wheeler, suggests that everything in the physical world, it, derives its existence from information, bit. In this view, the universe is not just describable by information, it is made of information. If that's the case, then the universe's origin could be seen as the moment this fundamental computation began, the initial state of this cosmic algorithm being set into motion. One of the most compelling aspects of the universe as a computational construct theory is its potential to offer a unified framework for understanding physics, particularly bridging the gap between general relativity and quantum mechanics. If the universe operates like a gigantic computer, then the laws of physics are its programming language and particles and fields are its data structures. Space and time themselves could be emergent properties of this computation, arising from the rules of how information is processed and related. This could explain the universe's inherent discreteness at the quantum level, the pixels or fundamental units of space and time we discussed earlier as an intrinsic feature of a digital computational reality. It's like finding the resolution limits of a computer screen, suggesting that reality at its deepest level has a finite, quantifiable information capacity rather than being infinitely continuous. This theory also provides a unique perspective on the fine-tuning problem. If the universe is a computational construct, its laws and constants, those precise values that allow for stars, galaxies, and life, could be seen as carefully chosen parameters within the program. Just as a software engineer sets specific variables to achieve a desired outcome, a cosmic programmer might have set the universe's constants to allow for complexity and consciousness. This could be interpreted as a form of intelligent design, but one expressed through the language of computation rather than traditional creation. Alternatively, if the universe is part of a larger multiverse generated computationally, then different runs of the program or different programs altogether could produce universes with varying parameters. We would simply be one of the successful runs, the result of a computation designed to produce self-aware beings capable of observing the output. The idea also intertwines with the simulation hypothesis, which we explored earlier. If our universe is a simulation, then it is by definition a computational construct. The universe as a computational construct theory takes this a step further, suggesting that even base reality might be fundamentally computational, implying an infinite regress of simulated realities or a foundational reality that is algorithmic at its core. This means that the universe's origin might not be a physical Big Bang, but the initialization of a cosmic program, the moment the grand algorithm began to execute, laying out the rules that would govern the subsequent unfolding of cosmic history. This provides a clean, elegant conceptual answer to the question of what came before the Big Bang, perhaps nothing but the unexecuted algorithm waiting for its initial command. However, the universe as a computational construct theory faces considerable philosophical and scientific challenges, proving that the universe is fundamentally information rather than deriving information from physical phenomena is a monumental task. What constitutes the computer that runs this cosmic program? Is it a physical computer in another universe, or is the computation itself the most fundamental aspect of reality? And if the universe is a computation, what is its purpose and who or what started it? These questions delve into areas beyond current scientific methodology. Furthermore, even if we can describe the universe in terms of information, demonstrating that it is information rather than merely having informational properties is a crucial distinction. Nevertheless, this theory pushes the boundaries of our understanding, inviting us to imagine a cosmos whose very existence is a testament to the power of computation. It suggests that the symphony of stars and galaxies, the intricate dance of particles, and the mystery of consciousness itself are all part of an infinitely complex, self-generating cosmic code, continually manifesting reality with every executed line. While the universe as a computational construct suggests our reality is a meticulously executed program, our 25th and final controversial theory drills down even further, redefining what we consider fundamental, the information universe. Imagine for a moment that the deepest, most irreducible constituent of all reality isn't matter, energy, or even space-time in the traditional sense, but information itself. This radical concept proposes that the entire cosmos, from the smallest subatomic particle to the largest cosmic structures, and even the very laws that govern them, are ultimately manifestations of information. The universe, in this view, is not merely describable by information or running like a computer. It fundamentally is a vast, self-organizing informational system, and its origin might be tied to the emergence or initialization of this fundamental information. This truly mind-bending idea stretches our understanding of existence to its absolute limits, suggesting that what we perceive as physical reality is merely the output of a cosmic information processing network. At the core of this theory lies the growing realization within advanced physics that information is far more fundamental than previously thought. Consider a black hole. When matter falls into it, it's seemingly lost. Yet, quantum mechanics insists that information cannot be truly destroyed. This conflict, known as the information paradox, has led many physicists to theorize that information about the matter is somehow encoded on the black hole's event horizon. This concept, formalized in the holographic principle, suggests that the information content of a three-dimensional volume can be entirely described by data on a two-dimensional surface. This implies a universe where information is conserved and critical, not just a byproduct of physical processes, but perhaps the underlying reality. If everything ultimately boils down to bits of information, then the Big Bang wasn't just an explosion of matter and energy, but the moment this cosmic information began to process and unfold its intricate patterns, leading to the universe we observe. The information universe theory finds a powerful ally in the concept of digital physics, which suggests that the universe is essentially a giant computer and its laws are algorithms. Proponents like Edward Fredkin and Stephen Wolfram argue that physical laws are not abstract mathematical statements, but actual computational rules that operate on fundamental bits of information to produce the universe. This isn't just an analogy, it's a claim about the intrinsic nature of reality. If reality is digital at its most fundamental level, then particles like electrons and quarks are not physical objects in the conventional sense, but complex information structures or states within this cosmic computation. Their interactions, their quantum properties, and their very existence derive from the execution of computational rules. This means that the universe didn't come from nothing, but rather from bits, from an initial informational state that then computed itself into the complex physical reality we inhabit. It's a universe that is self-executing, a cosmic program running itself, continuously generating reality byte by byte, or rather, bit by bit. This perspective naturally offers unique ways to understand some of cosmology's greatest mysteries. For example, the precise values of the fundamental constants of nature, the strength of gravity, the mass of an electron, the speed of light, which appear so exquisitely fine-tuned for the emergence of life, could be seen as the specific parameters or initial conditions of the cosmic program. If the universe is a computation, then these constants are not arbitrary values, but part of the carefully designed or naturally selected algorithm that governs reality. Similarly, the Big Bang singularity, where all known physical laws break down, could be reinterpreted not as a breakdown, but as the initial state or the boot-up sequence of this cosmic program, a moment of universal initialization from which all subsequent information processing flowed. This sidesteps the traditional problem of what came before the Big Bang by suggesting that nothing existed but the abstract informational potential or the unexecuted code waiting to be run. Furthermore, the information universe lends itself well to explaining concepts like quantum entanglement and non-locality. If information is truly fundamental, then the interconnectedness of seemingly distant particles could be a natural consequence of their shared informational blueprint or their derivation from the same computational thread. It also provides a framework for understanding complex phenomena like consciousness. If the universe is built from information, then consciousness might be an emergent property of highly sophisticated information processing, a self-aware algorithm or a complex pattern of information that becomes aware of its own existence within the cosmic computation. This elevates information from a mere tool of description to the very essence of being, suggesting that reality is not something physical that then processes information, but information that then manifests as physical reality. However, the information universe, as intriguing as it is, presents colossal challenges. Defining and measuring information in a way that is scientifically testable beyond simple data storage is incredibly complex. What is the cosmic computer running this program? Is it physical, or is the computation itself the ultimate reality? How can we distinguish between a universe that is merely like a computer and one that literally is a computation? The falsifiability of such a grand claim remains elusive. It requires a complete theoretical framework that can derive all observed physical laws from informational principles, which is still a distant goal. Despite these profound questions, the information universe theory represents the ultimate frontier of our quest for cosmic origins, pushing us to consider that the greatest mystery of all might not be what the universe is made of, but what fundamental information it began as and what cosmic code it is continually running. Phew, what an incredible journey we've taken together. From the infinitely repeating cycles of the Big Bounce to the chaotic burst of primordial black holes, and from the elegant dance of an ekpyrotic collision to the mind-bending notion of a universe that is fundamentally information or a computational construct. We've wrestled with the philosophical implications of a conscious universe and pondered the statistical inevitability of a multiverse bubbling with infinite possibilities. Each theory, no matter how outlandish it might seem at first glance, represents a monumental leap of human intellect, a valiant attempt to piece together the cosmic jigsaw puzzle that surrounds us. It's a testament to our insatiable curiosity, our audacity to comprehend the incomprehensible, and our relentless pursuit of truth in the face of profound mystery. We've seen how some ideas, like the steady-state theory, were once dominant but yielded to new evidence, while others, like the cosmic egg, hint at ancient intuitions surprisingly resonant with modern science. This exploration has highlighted something truly remarkable. The universe is far stranger, far more complex, and far more diverse in its potential origins than any single theory can fully encapsulate. The traditional Big Bang, while a cornerstone of modern cosmology, is just one piece of a much larger, more intricate, and far more mystifying puzzle. We've pushed the boundaries of what we thought was possible, questioning not just how the universe began, but what it even means to have a beginning. Is it a singular point in time, an endless cycle, a quantum fluctuation, or merely a phase transition in a much grander, multi-dimensional reality? These are not just academic questions for physicists. They are fundamental inquiries that shape our understanding of existence, our place within the cosmos, and the very nature of reality itself. They force us to confront the limits of our perception and the astonishing depth of the unknown that still lies before us. The beauty of these controversial theories lies in their ability to ignite our imagination and challenge our assumptions. They remind us that science is not about finding definitive, unchanging answers, but about a continuous process of questioning, exploring, and refining our understanding. Every new theory, every new piece of observational data, every conceptual breakthrough pushes the boundaries of our knowledge, leading us closer to a more complete picture of the cosmos. Whether our universe is a holographic projection, a self-creating entity, or even just one bubble in an infinite cosmic foam, the journey of discovery is perhaps the most profound aspect of our human experience. It's a continuous dialogue between observation and theory, a relentless pursuit of clarity in the face of cosmic enigma. So, after this whirlwind tour of the universe's most audacious origin stories, which theory left you utterly spellbound? Did one particular idea resonate deeply with you, or perhaps spark a brand new question in your mind? Do you have your own wild, untamed idea about how our universe came to be, one that challenges everything we've discussed? We are genuinely eager to hear your thoughts, your insights, and your own cosmic musings. Share your favorite theory or propose your own in the comments section below. Let's keep this cosmic conversation going, because the more minds we bring to these fundamental questions, the richer and more expansive our collective understanding of the universe becomes. And if you enjoyed this mind-bending exploration, please give this video a thumbs up to help us reach more fellow cosmic adventurers. Don't forget to subscribe to our channel for more deep dives into the mysteries of space, and be sure to hit that notification bell so you won't miss our next journey into the unknown.